Before humans, before cities, before history itself, this coastline belonged to giants. Not just big reptiles, but the biggest creatures to ever walk the earth. On a warm Cretaceous evening along what will one day be the Yucatan Peninsula, the world is calm. The sun hangs low over a shallow inland sea, turning the water to molten gold. Hadrosaurs wade at the edge, their duckbills dipping and lifting in a slow, practiced rhythm as they crop ferns and flowering plants that fringe the shore. Ceratopsians, heavy with horn and frill, move through palm-like cycads just beyond the beach, their silhouettes black against the orange light. Above them, pterosaurs glide on outstretched wings, riding columns of warm air as easily as seabirds. The air is thick, humid, alive with the constant buzz of insects and the distant calls of animals that have ruled this era for more than 150 million years. We step back hundreds of millions of years into a world of scale we can barely imagine. Forests of broad-leafed angiosperms and towering conifers form a dense green wall behind the sand. Flowering plants paint the undergrowth with color, attracting beetles, wasps, and early bees that stitch the evening together with their droning flight. In the nearby waters, mosasaurs and schools of fish patrol the reefs, while ammonites drifted in the dimming light, their coiled shells catching the last reflections of day. This late Cretaceous world is not fading, it is thriving. A tyrannosaur steps from the trees, massive skull swinging as it surveys the shoreline. Each footfall presses deep into the damp sediment, leaving tracks that, in another age, will harden into stone. It pauses to drink, sharing the water's edge with the very herbivores it hunts. For a moment, there's only the soft slap of waves, the rustle of leaves, and the low rumble of distant surf. This looks like peace. It feels eternal, but something is wrong. High above the horizon, just where the first stars should appear, there is a point of light that is too bright, too steady, sitting low in the sky like an unfamiliar evening star. Some animals notice. A flock of early birds explodes from the canopy for no obvious reason, wheeling and calling as if startled by a sound we cannot hear. Small mammals slip deeper into their burrows, claws scraping at the packed earth. Crocodiles linger half-submerged in quiet backwaters, eyes just breaking the surface, as if waiting. We cannot see it yet, but far out beyond the curve of the planet, a mountain of rock and metal is racing toward Earth faster than a rifle bullet. In a matter of hours, it will strike with the power of billions of nuclear bombs, unleashing the most violent single day this planet has seen in hundreds of millions of years. This is not only the end of the dinosaurs, it is a global reset. Join us as we set the stage for impact and ask a single, haunting question. When that asteroid hits, what happens next? From the first blinding flash to the moment true night falls, how does Earth change? This is our planet, this ancient shoreline, minutes before everything changes. To understand what is about to be torn apart, we first have to see the world as it was, not in ruins, but at its peak. A living, breathing planet filled with giants, wrapped in warmth, and lit by a sun that seemed it would shine on them forever. 66 million years ago, Earth was a greenhouse world. There were no polar ice caps. Sea levels stood far higher than today, and vast, shallow oceans flooded the edges of continents. Warm waters crept inland, turning what are now dry heartlands into inland seas that shimmered under a humid sky. This was not a scattered patchwork of habitats, but a continuous, thriving biosphere. If we look down from above, the continents are both familiar and strange. North America is split in two by the Western Interior Seaway, a broad, shallow sea stretching from the Arctic to the Gulf of Mexico, dividing eastern forests from western floodplains. South America and Africa have largely gone their separate ways, each carrying its own evolving cast of creatures. Far to the east, India is a solitary landmass on a northward journey, racing toward Asia. And at the impact point itself, The Yucatan region lies as a low tropical carbonate platform, surrounded by a warm, clear ocean rich in reefs. On land, this ancient world belongs to the biggest creatures to ever walk the earth. In the southern hemisphere, massive titanosaurs like Argentinosaurus roam river valleys and coastal plains, their necks sweeping over forests as they strip foliage by the ton. Across western North America, horned ceratopsians, such as Triceratops, crowd floodplain meadows, while duck-billed hadrosaurs graze in herds so large they reshape entire landscapes. Stalking among them are tyrannosaurs, apex predators with skulls as long as a person is tall, and around their feet dart smaller theropods and sleek, feathered raptors. Yet dinosaurs are only part of this colossal tapestry. Early birds flit between branches. Small shrew-like mammals hide in the undergrowth and burrows, feeding on insects, seeds, and eggs. In rivers and swamps, crocodilians wait motionless beneath the surface. Offshore, the western interior seaway and global oceans are ruled by mosasaurs and plesiosaurs, marine reptiles hunting amid schools of fish and coiled chambered ammonites. Coral and sponge reefs support dense communities of invertebrates, algae, and fish, forming underwater cities of life. The land itself is lush. Dense conifer forests cloak uplands, while ferns and cycads fill the shaded understory. Increasingly, flowering plants dominate riverbanks and coastal plains, their blossoms attracting insects and early pollinators, their fruits feeding herbivores. These plants, in turn, support complex food webs, from tiny leaf eaters to colossal sauropods, from nectar-sipping insects to the predators that prey on them. Fossils from this final Cretaceous period tell a clear story. This was not a world in slow decline. Dinosaur bones, eggs, and trackways remain abundant right up to the extinction boundary, showing thriving, widespread populations with no sign of an inevitable fade-out. Life is diverse, adaptable, and deeply entrenched, and it is all interconnected. Dust and spores ride high winds between continents. Ocean currents carry heat, nutrients, and larvae across entire basins. Migrating animals link distant ecosystems. In this way, we step back hundreds of millions of years and see a world of scale we can barely imagine, yet one held together by a few simple threads: sunlight, climate, and the steady rhythm of seasons. Join us as we hold that image in our minds, because it hides a quiet fragility. What happens when the light itself is choked off? When the warm seas cool and the global engine of photosynthesis stalls? In the next moments of our story, a single impact will strike this stable, abundant Earth, and those same connections that once spread life will spread catastrophe. But that stability is already an illusion. Far out in the darkness, long before this peaceful late Cretaceous evening, a small silent killer has been on its way. Not a rogue planet, not a star. A fragment of rock and metal, only about 10 to 12 kilometers across, comparable in size to a major city, yet massive enough to rewrite the story of life on Earth. For millions of years, this asteroid wandered the cold reaches of the solar system. Most likely, it began in the outer asteroid belt, part of a population of ancient debris left over from planet formation. There, subtle gravitational tugs from Jupiter or a distant collision with another body slowly nudged its path. Each orbit, its trajectory shifted by fractions of a hair's breadth, until by chance alone, its new course intersected the orbit of our planet. When we step back hundreds of millions of years in our minds and watch this process in fast motion, we see a quiet choreography. Resonances with Jupiter's gravity amplify tiny motions. A once safe orbit becomes elongated. The asteroid's path crosses Mars, then approaches Earth's. Nothing about this looks dramatic when viewed over eons, yet this is how a world of scale we can barely imagine can be changed by something that, in space, is almost invisible. Now draw back with us and look at Earth from space, A blue and white sphere fills the frame, clouds swirling over continents where the biggest creatures to ever walk the Earth browse and hunt. Against that colossal disk, the impactor is only a pinprick of light, racing in at roughly 20 kilometers every second, more than 70,000 kilometers per hour. It looks harmless. It is anything but. At that speed, its kinetic energy is staggering, equivalent to billions of Hiroshima bombs detonating at once, far beyond the force of any volcanic eruption or human weapon. Rock and metal, frozen for ages, have become a compressed package of pure devastation. How can something so small do so much? Because energy scales with velocity squared, and this object is moving faster than any storm, any bullet, any eruption we have ever known. On the ground, no one can know. Dinosaurs have no telescopes, no mathematics of orbits, no warning systems. The evening sky over the Yucatan region looks ordinary. Stars emerge. Waves roll onto tropical shores. Only in the final seconds will a new blinding point appear low on the horizon, brighter than the sun. We call the impactor Chicxulub, after the structure it will carve beneath what is now Mexico's Yucatan Peninsula. Today, that crater lies buried under younger sediments and partly beneath the Gulf of Mexico, more than 150 kilometers across, its rim fractured and hidden. We do not see the wound with our eyes. We trace it with seismic surveys, gravity maps, and drilled cores. Around the world, a thin layer in the rocks tells the same story. A spike of iridium, rare in Earth's crust, but common in asteroids. Grains of shocked quartz, their crystal lattices scarred by unimaginable pressures. Tiny glassy spherules, once droplets of molten rock thrown high into the atmosphere. Together, these clues let scientists set the stage for this night of extinction. In space, the distance shrinks. Hours become minutes. Minutes will soon become seconds. Late Cretaceous Earth turns beneath an invisible crosshair, still vibrant, still loud with life, utterly unaware that the next heartbeat of geological time will end an era. 10 turned to 31. Ground zero chosen by chance, the future Yucatan Peninsula. As the crosshair tightens, we descend toward a very specific place on this ancient world. Not a barren wasteland, but a warm, shallow tropical sea, draped across what will one day be called the Yucatan Peninsula. From orbit, it looks peaceful. Turquoise water, pale carbonate platforms like submerged continents of chalk, low forested coasts tracing the edge of a quiet inland sea. When we step back hundreds of millions of years in our imagination, this is not the solid limestone land we know today, but a broad marine shelf only a few hundred meters deep at most. Sunlight reaches the seafloor. Reefs and sandbars break the waves. Between them, clear water blooms with plankton, tiny floating plants and animals that build delicate shells of calcium carbonate. On nearby islands and coastal plains, dinosaurs move through humid forests, sharing the shoreline with crocodiles, turtles, and flying reptiles that launch from the cliffs and glide over the surf. Beneath this calm surface lies the crucial secret. Layer upon layer of limestone, dolomite, and other carbonates pack the crust, the compressed remains of countless generations of marine life. Mixed into these are thick beds of evaporites, including gypsum and other sulfate-rich rocks laid down when earlier seas repeatedly evaporated. This is not just ordinary crust. It is a colossal chemical reservoir, waiting to be unlocked in an instant. Why does that matter? Because when an asteroid strikes rock like this with unimaginable energy, it does not simply shatter it. It vaporizes it. Carbonate turns into carbon dioxide gas. Sulfates flash into sulfur-bearing vapors that can form reflective aerosols high in the atmosphere. An impact into bare continental granite would still be devastating. A deep ocean impact would throw water and mud skyward. But here, in this carbonate and sulfate-rich shelf, the collision is primed to inject both greenhouse gases and sun-blocking particles into the sky on a global scale. Join us as we consider the cruel mathematics of chance. The asteroid did not choose this target. Its path was set long before these reefs existed. Yet, in terms of climate disruption, this was one of the worst possible places on Earth it could have struck. The water is shallow enough that the incoming body will punch straight through the sea, excavating the seafloor and the loaded crust beneath. At the same time, there is still enough water above to be hurled outward as massive walls of displaced ocean, spawning mega tsunamis that will race across entire basins. Today, we can read the scar it left behind. Gravity anomalies outline a buried circle more than 180 kilometers wide. Seismic imaging reveals a multi-ring impact structure hidden under younger sediments. Drill cores bring up shocked quartz, melted rock, and a distinctive sequence of tsunami deposits. All of it converges on one conclusion. This quiet tropical shelf became ground zero for an extinction. Now, in our reconstruction, we return to the surface one last time. The reefs are bright. The coastal forests are loud with life. The biggest creatures to ever walk the earth still roam the margins of this inland sea. And above them, the asteroid now spans the sky, seconds away from slamming into this carbonate platform. In the next heartbeat, this peaceful scene will be erased, and a world of scale we can barely imagine will change forever. In that final heartbeat, the peaceful inland sea becomes a target. The asteroid that has grown from a star-like point to a looming disk now tears into the upper atmosphere faster than a rifle bullet, faster than sound itself can move out of its way. Air in front of it has nowhere to go. It is squeezed, crushed, driven to such pressures that it heats to incandescence. From the ground, the sky splits. A single blinding streak carves from horizon to horizon, brighter than lightning, brighter than the midday sun. Shadows sharpen in an instant. Forest leaves curl and smoke from the radiant heat alone. For a few terrible seconds, every eye that looks up is seared. This is not just a falling rock. This is a mountain of stone wrapped in fire. When it reaches the surface, it does not simply hit the ground. It explodes. In less than a second, almost all of its colossal kinetic energy is forced into the crust and the shallow sea. Rock behaves like liquid under that stress. Carbonate platforms, sediments, and seawater are crushed, sheared, and driven downward, then hurled outward as if the top of the planet has turned to shrapnel. At the point of contact, temperatures soar to thousands of degrees. Rock, metal, and ocean water do not merely melt. They vaporize, forming a superheated fireball of glowing plasma that balloons outward and upward. Join us as we imagine standing at the edge of this forming abyss. In front of you, the shoreline is simply gone, replaced by a rising sphere of white-blue light that swallows clouds and sky. In the first minutes, a transient crater, perhaps 100 kilometers across, yawns open, then collapses and rebounds. Rings of fractured rock rise and fall like slow-motion waves in stone. Blocks the size of city blocks are thrown hundreds of kilometers away. Some debris is launched on suborbital arcs, leaving Earth's lower atmosphere entirely before falling back on distant continents. Within hundreds of kilometers, there is no time to flee. Everything is incinerated or pulverized. Dinosaurs along the coast, entire forests, reef systems, and seafloor communities vanish in a flash, erased so completely that only shocked minerals and glassy droplets will whisper that they ever existed. This is extinction delivered in an instant. The violence does not stay local. Shock waves drive through the crust as seismic waves equivalent to magnitude 10 or even 11 earthquakes, shaking the entire planet. Through the air, a supersonic blast front races outward, flattening trees, stripping flesh, and igniting anything that can burn. For a brief, blinding interval, the fireball outshines the sun itself, casting harsh, alien light across much of the hemisphere. Can you imagine midday turning into something brighter yet deadly, as if a second star has descended to Earth? Far beyond the immediate kill zone, creatures pause, dazzled and terrified as the sky glows with an unnatural dawn. Then we pull back. The fireball blossoms into a towering, mushrooming plume over the Yucatan, a pillar of vaporized rock, ash and steam punching through the atmosphere. From space, Earth now bears a glowing wound, a radiant scar where a tranquil sea once lay. In the darkness beyond this burning circle, the first night of a transformed world is about to begin. Up close, that glowing wound is not just light in the sky. It is a zone of instant, total annihilation. Within a radius of several hundred kilometers around Chicxulub, from the Yucatan coast, deep into the Gulf and across nearby landmasses, the surface of Earth itself is no longer a place where large life can survive. Along the low coastal forests and plains, the change is brutal and immediate. One moment, hadrosaurs browse among cycads and flowering plants. Small predators move through the undergrowth. Insects hum in the warm Cretaceous air. The next, a wall of superheated gas and pulverized rock slams outward faster than sound. Trees do not just fall, they vanish into splinters and vapor. Dinosaurs are not simply killed, they are torn apart, burned and swept away in a hurricane-force blast that strips soil, plants and bodies into a single roiling cloud. Where that blast meets the shallow sea, an equally violent transformation unfolds. The impact has already driven a colossal cavity into the ocean, displacing much of the water column and excavating the seafloor to depths of kilometers. For marine life, from delicate plankton drifting near the surface to massive mosasaurs patrolling the shelves, there is no warning and no refuge. Pressure spikes shatter internal organs. Shockwaves fracture bones and shells. Temperatures soar so quickly that water flashes to steam, scalding and disintegrating living tissue in an instant. Above, the atmosphere itself becomes a weapon. The shockwave races outward as a supersonic wall of compressed air, flattening everything in its expanding ring. Before we even reach the crater rim, forests are snapped flat like fields of grass under a colossal hand. Structures of any kind, from fragile nests to thick-trunked trees, are ripped apart. In some places, the blast scours down to bedrock, erasing not just organisms, but the very surfaces they stood on. Can we truly picture a landscape where even shadows have nothing left to cling to? Then, within minutes, the sky begins to fall. Vast quantities of rock, glassy droplets, and molten beads called tektites arc back down, raining over the near zone. Each fragment carries heat. Each impact adds sparks to an already blazing inferno. Any remaining pockets of structure, any creature somehow shielded from the first blast, are pelted, crushed, and burned as this incandescent hail completes the destruction. Even the hidden places fail. Underground burrows collapse under the passing shock, their air superheated, their walls liquefied or compacted. Shallow underwater refugees are overwhelmed by violent pressure waves, boiling temperatures, and slumping sediments that entomb or grind everything within. This is not just the death of individuals, it is the physical unmaking of an ecosystem. In less time than it takes you to read a single sentence, a thriving coastal world of giants and smaller creatures alike is converted into a blasted, molten, cratered wasteland. Join us as we step back hundreds of millions of years in our minds and try to grasp that speed of change, an entire region flicked off like a switch. Yet beyond this circle of devastation, thousands of kilometers away, the ancient world still looks almost normal. Herds move through forests. Pterosaurs wheel over quiet seas. Perhaps there has been a blinding flash on the horizon, a distant tremor underfoot, but life goes on, for the moment. This contrast between total erasure at ground zero and the fragile calm elsewhere will set the stage for what comes next. Because while the immediate kill zone has already paid the full price, the rest of Earth has only received a warning. What happens when the consequences of this impact reach those still intact, unaware ecosystems? Elsewhere on this ancient world, that distant tremor does not stay distant for long. The blow at Chicxulub has already done more than erase a coastline. It has struck the entire planet like a hammer on a colossal gong. When a stone hits a pond, ripples race outward in perfect circles. Here, the stone is a 10-kilometer asteroid, and the pond is Earth's solid crust and semi-molten mantle. Seismic waves surge away from the impact in all directions, compressing and stretching the rocks they pass through, reflecting from boundaries deep inside the planet and turning the whole globe into a vibrating body. Earth is literally ringing like a bell, its interior carrying the memory of the strike. Close to the crater, the shaking reaches unimaginable intensity. We are not talking about the largest earthquakes ever recorded by humans. We are talking about events beyond our direct experience, magnitude 10 or higher, releasing energy that dwarfs any known fault rupture. Near ground zero, the crust lurches, heaves and fractures. Further out, the waves weaken, but still arrive as violent, rolling convulsions that sweep across continents within minutes. Join us as we follow those waves to a distant shore, perhaps the western edge of North America. Here, forests of hadrosaurs and horned giants still move through their routines, unaware of what has happened beyond the horizon. Then the ground bucks, not once but in long, punishing bursts. Trees sway so far they nearly touch the soil. Rock faces that have stood for millions of years suddenly peel away from canyon walls, collapsing in roaring landslides. Riverbanks slump and crack, sending curtains of mud and vegetation sliding into the water. Dinosaurs stagger, call out, and scatter as the landscape itself turns hostile beneath their feet. Across the Atlantic, in Cretaceous Africa, the story is the same. Herds along broad river deltas feel the shock as the saturated ground beneath them liquefies, grains of sand and silt losing their grip and behaving like a fluid. Whole stands of forest tilt and topple. Burrows collapse. Channels are choked or abruptly diverted, setting the stage for new river courses in the hours and days to come. In these low, wet regions, the boundary between solid land and water blurs in moments. Above all this, the air carries its own record of the catastrophe. The initial blast has already launched pressure waves into the atmosphere, and these atmospheric shock fronts now race around the globe at jetliner speeds. Minutes to hours after the first unnatural flash lit the sky, distant regions feel sudden, hammering gusts of wind, preceded or followed by sharp, rolling booms that echo off cliffs and forests. Even where the ground shaking is modest, the sky itself seems to punch down. Beneath the oceans, the same seismic violence destabilizes steep submarine slopes. Sediments piled for ages on continental margins slump and cascade, forming underwater landslides that displace colossal volumes of water. These collapses help generate new tsunamis and amplify existing ones, sending additional walls of water racing outward along with the primary impact waves. What begins as a single blow becomes a chain reaction of hazards. Step back hundreds of millions of years in your mind, and you can see this entire planet-scale response at once. Crust flexing, seas sloshing, air ringing, a world of scale we can barely imagine. This is not a local disaster. The biggest creatures to ever walk the Earth are now caught on a globe that is shuddering to its core. And yet, while cliffs are still collapsing and forests are still sinking into liquefied ground, something even more imposing is forming beyond the horizon. Out across the heaving oceans, vast walls of displaced water are gathering speed, racing toward distant coasts. The shaking is only the prelude. What happens when the seas themselves rise up to finish what the asteroid began? Before humans, before cities, before history itself, there were moments when the oceans themselves became weapons. This is one of those moments. As the asteroid slams into the shallow Yucatan Sea, it does not simply make a crater in rock. It punches a void in water. In an instant, billions of tons of seawater are blasted aside, heaved upward, and dragged downward into the collapsing cavity. Near the forming Chicxulub crater, The sea surface does something no living eye has ever witnessed. It disappears, then rears back as a colossal ring of water hundreds of meters high. Not just big waves, but moving cliffs. These are impact tsunamis, born from a blow that shook the entire Earth. From this epicenter, walls of water radiate outward across the Gulf of Mexico. They race at jetliner speeds, guided by the depth of the seafloor, funneled through straits, spilling into the western interior seaway that once split North America in two. As they spread into the Atlantic and beyond, the waves lose some height, but not their power. Even thousands of kilometers away, they still rise tens of meters, enough to erase coastlines in a single pass. In this late Cretaceous world of broad low-lying shores, where can anything run? Join us as we follow one of these giants of water into the interior seaway. The shoreline here lies where the Great Plains will one day be. On a humid coastal plain, herds of hadrosaurs and horned dinosaurs graze near mangrove-fringed shallows, unaware that the horizon is hiding a moving wall. There is no towering breaker curling overhead. Instead, the sea level simply begins to climb, faster and faster, choked with shattered trees, broken shells, and boulders ripped from the seabed. Within minutes, the gentle beach becomes a roaring current, surging tens of kilometers inland, sweeping animals, forests, and soil into a single chaotic flow. This is not a single blow, and then silence. As these tsunamis strike continental margins, they reflect and refract, bouncing off shelves and island chains, splitting into new fronts. One wave crashes ashore, retreats in a violent backwash, then another arrives, and another. For hours, coasts around the world endure this pulsing assault, water rushing in and tearing back out, grinding everything into tangled debris. What does such violence leave behind? In the rocks of this era, we can still read the answer. Geologists find thick, jumbled layers of sand and gravel where quiet mud should be, stacked with rip-up clasts torn from older sediments, and mixed beds of marine shells, land plants, and dinosaur bones. These strata record powerful back-and-forth movement, the signature of tsunamis that did not merely visit the land, but tried to claim it. Marine ecosystems suffer alongside the land. Shallow reefs are smashed by sediment-laden torrents. Coastal nurseries where fish, ammonites, and marine reptiles once thrived are buried or scoured to bedrock. Near shorelines, many populations are simply erased in one catastrophic period of hours. Yet even as the seas rise and fall, another threat is preparing to descend. High above this drowning world, ejecta and molten glass are circling the planet, about to turn vast regions of Earth into an oven. That oven is already lit. High above the impact site, the asteroid has blown a column of Earth itself into the sky. Rock, water, and soil are vaporized into a colossal plume that punches through the atmosphere and expands outward, wrapping the planet in a glowing shroud. Some of this material is blasted all the way into space, arcing around our ancient world before falling back. For a brief, terrible period, Earth is surrounded by its own torn-up crust. As this incandescent cloud races around the globe, it begins to cool. Vaporized rock condenses into tiny glassy droplets, perfect spheres that freeze in mid-flight. We call them tektites and spherules, and they number in the trillions. Mixed among them are larger, jagged chunks of ejecta, torn from deep within the crust and lofted thousands of kilometers high. Within minutes to hours, gravity calls all of it home. Now the physics of re-entry takes over. Each grain, each bead of glass, each fragment of stone plummets back through the atmosphere at immense speed. Friction heats their surfaces until they glow, then blaze. Individually, they are like grains of sand in a desert storm. Collectively, they form a shell of incandescent projectiles that turns the sky into a radiant furnace. They do not just burn themselves, they heat the air, which in turn pours infrared energy downward like a global broiler. Far from the crater, where no one can see the ruined coastline of Chicxulub. The first sign is subtle. The sky, already hazy from dust, begins to darken in the middle of the day. Then the pattern changes. Lines of light appear, thin at first, then multiplying, until the heavens seem to be filled with shooting stars. We step back hundreds of millions of years in our minds and ask, what would it feel like to stand there under a firmament of fire? Soon, the display stops being beautiful. The streaks thicken into fiery arcs, and a fine hail begins to fall. Hot glass beads, no larger than sand grains or peas, patter onto leaves, into shallow seas, across open plains. Ash drifts down with them, coating the backs of the biggest creatures to ever walk the earth. Surface temperatures climb as radiant heat pours down. Dry ferns, conifer needles, and flowering shrubs reach their ignition point. Across continents, forests burst into flame almost at once, not because sparks leap from tree to tree, but because the air itself has been heated from above. Some models suggest that for a short period, exposed ground temperatures soar high enough to be lethal to large animals caught without shelter, even thousands of kilometers from the impact. Can you imagine herds of giants suddenly trapped between burning horizons and an invisible wave of heat? This rain of fire leaves a permanent mark. The tektites and ash settle into a thin, global layer of clay enriched in iridium from the asteroid, mixed with shocked minerals and glassy spherules. Today, geologists trace that razor-thin band at the KEPG boundary around the world and know they are touching the moment of extinction. But as the last molten beads fall and the first great firestorms rage, a different transformation begins overhead. Smoke from burning continents, soot from incinerated forests, and fine dust from the impact rise and spread, blotting out the very sky that burned the surface. The world that was briefly turned into an oven is about to face the opposite fate, a darkness so deep and so long that it will challenge the survival of almost everything left alive. What happens when the fires fade and day itself disappears? The answer comes almost immediately. As the incandescent veil of ejecta wraps around the planet, the response on the surface is as sudden as it is terrifying. Forests do not simply catch fire one by one. Entire continents ignite. Across what will one day be North America, curtains of conifer forest erupt into flame almost in unison, crowns flashing from dark green to blinding orange in seconds. In Gondwanan fragments to the south, from the humid lowlands of ancient South America to the open shrublands of Africa and India, fire fronts surge outward in lines that stretch for hundreds, even thousands of kilometers. This is not a patchwork of wildfires. This is the first global wildfire in Earth's history. The fuel is ready and waiting. Late Cretaceous landscapes are packed with dense vegetation, resinous conifers loaded with flammable sap, thick undergrowth and carpets of dry leaf litter and dead branches accumulated over seasons. When radiant heating from the superheated sky meets this material, it does not smolder. It flashes. Crown fires roar through the treetops, leaping from canopy to canopy, throwing off whirling firestorms that move faster than many animals can run. Join us as we step back hundreds of millions of years in imagination and stand just for a moment inside this inferno. The sensory world for any surviving animal is almost unrecognizable. The air is thick with choking smoke that scours lungs and eyes. Ash falls like snow, coating scales and feathers in a gray, gritty mantle. All around, the constant crackle of burning branches blends into a continuous roar, like an ocean of flame rolling through the forest. Above, the sky is no longer blue but a dim, seething orange, the sun reduced to a dull, swollen disk behind layers of smoke and dust. In this chaos, the biggest creatures to ever walk the earth are suddenly fragile. Large, exposed dinosaurs that dominated these ecosystems only hours before now find themselves trapped between advancing fire lines. Herds of hadrosaurs and ceratopsians flee downhill or toward rivers, but many collapse from heat stress before they reach safety. Massive theropods, apex predators of their era, are just as vulnerable to superheated air and suffocating smoke. Without access to deep water, burrows, or sheltered lowlands that remain relatively cool and moist, their size offers no protection at all. How do you outrun a horizon that is on fire? Yet even this colossal event is not perfectly uniform. Wet regions, floodplains, coastal wetlands, and rain-soaked pockets of forest resist ignition. Some patches of vegetation survive, charred at the edges but unburned within. However, the overall effect is still a planetary pulse of combustion. Soot, ash, and blackened organic particles billow upward in towering pyrocumulus clouds, then are thrust even higher by the combined heat of millions of fires. Enormous amounts of black carbon are lofted all the way into the stratosphere, where there is no rain to wash them out quickly. There, this fine, dark dust will linger, scattering and blocking sunlight for years, far longer than ordinary smoke could. This is not speculation alone. At the KPG boundary, geologists find charcoal-rich layers and soot deposits around the world, a thin but unmistakable signature of global biomass burning at or near the time of impact. Those ancient black streaks in the rock record are the fossilized shadow of this night of fire. As the first catastrophic day leans toward night, the last independent flames merge into a continuous, smoldering glow. The planet is now wrapped in a veil of dust, soot, and aerosols that circles the globe. Set the stage for a world of scale we can barely imagine. What happens when that veil thickens? The light fades further, and the age of warmth gives way to an impact winter that will test every remaining survivor. As that veil thickens, the damage moves from the ground to the sky itself. Above the burning forests and boiling seas, the atmosphere becomes the main battlefield. To understand what happens next, we have to look up through the layers of air that surround this wounded Earth. Closest to the surface is the troposphere, the restless layer where our weather lives, where clouds form, rain falls, and winds churn. Above it lies the stratosphere, colder, calmer, stratified into stable sheets of air. Here, particles can drift for months or even years without being easily washed out by storms. Higher still, the thin mesosphere brushes the edge of space. In the calm of these upper layers, every grain of dust, every droplet of aerosol suddenly matters. When the asteroid struck, it did not simply blast sideways. It punched a colossal plume straight up through all of these layers. Vaporized rock, droplets of molten glass, and fine mineral dust shot into the stratosphere and beyond, some grains flung into the mesosphere before gravity slowly tugged them back. Sulfur-rich rocks from the Yucatan vaporized, then cooled into sulfate aerosols, tiny droplets capable of scattering sunlight far more efficiently than ordinary dust. At the same time, the surface of the planet is on fire. Wildfires race across continents, feeding on the dry, late Cretaceous vegetation. The rising heat powers towering convection columns, smokestacks that pierce the troposphere and inject black carbon soot into the stratosphere. This soot is darker than the surrounding dust, a light-absorbing pigment now painted across the upper sky. High-altitude winds begin to spread these particles around the globe, knitting together local disasters into a single, global shroud. Over the first day, the change in the sky would be unmistakable. Morning might begin with a harsh, glaring sun over the impact hemisphere, its light already softened by a thin haze. By midday, that same sun becomes a pale, blurred disk, like a bright coin seen through frosted glass. As more dust, sulfate aerosols, and soot accumulate overhead, the light shifts toward red and brown, a perpetual late sunset that never quite brightens. Can you imagine midday shadows that look like evening, even as the clock still says noon? This is not yet complete darkness everywhere. On the far side of the planet, away from the immediate plume, you could still read the landscape, still see colossal silhouettes of the biggest creatures to ever walk the Earth. But photosynthesis is already faltering. Plants near the impact hemisphere receive only a fraction of their former energy. In a world where giant herbivores depend on constant growth, that dimming is an invisible countdown. The aerosols play a double game. Locally, where soot absorbs sunlight, the upper atmosphere can warm, altering winds and trapping some heat below. Yet globally, the combined dust and sulfate veil reflects and absorbs incoming solar radiation before it ever reaches the surface. Less sunlight, it means less heat out. Climate models show surface temperatures plunging as this impact winter takes hold, an echo of the nuclear winter scenarios we fear in our own era. Join us as we follow this drop into cold. As the first true night falls after the impact, the darkness that spreads across the planet will not be an ordinary rotation into shadow. It will be the opening act of a long, artificial night, one that will last not hours, but months. What does a world of scale we can barely imagine look like when even daylight is stripped away? And now, as that artificial night begins to descend, we need to slow time down. Before the darkness fully claims the planet, there are still a few hours of daylight left, and they are unlike any others in Earth's history. Impact comes near local midday over what will one day be the Yucatan Peninsula. In an instant, the late Cretaceous sky above Chicxulub blooms into a second sun, a fireball hotter than the surface of the real one. Shockwaves rip outward through air, rock, and ocean. Within minutes, tsunamis rise like moving cliffs, and a curtain of vaporized stone and molten glass is thrown high into the atmosphere. While this unfolds, the planet keeps turning. Daylight elsewhere does not pause. On the impact-facing side of the globe, the catastrophe happens under a still visible sun. Forests in North America, the Caribbean, and parts of South America are lit by a harsh, bleaching light. The blast wave arrives as a wall of wind, flattening trees, tearing skin, stripping leaves. Above, the sky shifts from deep blue to a sickly gray-brown as ejecta begins to fall back through the atmosphere, each grain a tiny ember. It is still day, but the quality of that day is changing by the minute. As the hours pass, this strange twilight spreads eastward with the rotation of the planet. Join us as we track it across an ancient Atlantic toward the lands that will become Europe and Asia. There, it is already afternoon. Sauropods and hadrosaurs move through river valleys bathed in slanting golden light. Pterosaurs ride thermals, and small mammals watch from the shadows. At first, the only warning is subtle: a high haze that dulls the sun, a faint metallic tang in the air, a distant, continuous rumble in the ground. By mid-afternoon, the sun weakens further, as if someone has placed layer after layer of smoked glass in front of it. Temperatures begin to dip, not dramatically yet, but enough that warm-blooded animals fluff feathers and fur. Herds grow restless. Some dinosaurs lift their heads and call more often, their vocalizations echoing through forests that suddenly feel unfamiliar. Birds take to the air in erratic bursts, circling without clear direction, then diving for cover as the sky darkens in unnatural bands of brown and red. In wetlands and slow rivers, crocodilians slide into deeper water, their eyes just breaking the surface, sensing pressure waves and distant quakes. Burrowing mammals retreat underground, sealing tunnels behind them. Insects disappear into soil and rotting logs. Aquatic life in deeper lakes and channels, insulated by meters of water, continues its ancient routines, unaware that the giants above have entered their final hours. On the far side of the planet, in regions still enjoying morning or early afternoon, life goes on almost normally. The sun shines, though perhaps with a slightly reddish cast. Clouds form in odd, smeared patterns. Do distant hadrosaurs pause at the shoreline, puzzled by a low, rhythmic swell that does not match the usual tides? Do pterosaurs circle higher, sensing subtle changes in upper air currents? For now, death is mostly a rumor carried through the atmosphere. But as Earth turns, even these places are drawn toward a new kind of evening. The first sunsets after impact are not gentle fades from blue to orange. They are violent spectacles, with the sun sinking behind a horizon stained blood red and purple by ash, soot, and dust. The colors are breathtaking, but they are the colors of global combustion. In our representative valley in ancient Eurasia, the last normal day of the dinosaurs is ending. The sun, now a dim copper coin, struggles toward the horizon. Shadows lengthen, but instead of cooling blues, the sky above is already a heavy, roiling brown. The air smells of smoke from fires thousands of kilometers away. Leaves drift down, not in autumn's slow surrender, but scorched and curling at the edges. Herds press closer together. Some animals try to bed down early, confused by the failing light. Others remain standing, heads low as if waiting for a cue that never comes. The predictable rhythm of the Mesozoic era, bright days, star-filled nights, seasons cycling across millions of years, has been broken in a single afternoon. As the sun finally slips below the horizon, true night does not reveal a canopy of familiar constellations. Instead, the sky is a dark, churning ceiling, already thick with ash and dust. No stars, only a faint, hellish glow where distant fires rage beyond the curve of the Earth. We have reached the first night after the dinosaurs' extinction, but the most lethal effects of this impact winter have not yet fully arrived. What happens when this unnatural dusk locks into place and the world of scale we can barely imagine must try to survive without the sun at all? Now true night finally falls. Not the gentle, familiar darkness we know, but a lid slamming shut over the planet. In many places, the sky is not sprinkled with stars at all. It is a single suffocating sheet of black and dark brown, as if the heavens themselves have turned to stone. Here and there, far beyond the horizon, dull red glows pulse and fade. Those are forests, peat beds, and whole swamps still burning, their flames reflected off clouds of ash and soot. Instead of constellations, survivors see only these distant wounds of light, smeared across the lower sky like embers trapped behind glass. For any creature that lifts its head to look, the message is unmistakable. The cosmos has gone out. Dust, soot, and thick storm clouds now wrap the Earth in layer after layer of shadow. Starlight cannot punch through. Even the full moon, if it rises at all, is reduced to a vague, rusty disk or disappears entirely. In many regions, this first night is as dark as the deepest chamber of a cave. You could hold a massive sauropod skull at arm's length and not see your own hand in front of it. In that blackness, sound takes over. The ground mutters with distant aftershocks as the crust continues to settle from the colossal blow at Chicxulub. Far away, tsunamis that had raced across oceans now crash back off flooded coasts. A heavy, rhythmic thunder in the unseen distance. Closer to the impact side of the planet, entire horizons crackle and roar as wildfires race through ancient conifer and angiosperm forests. A continuous, low growl punctuated by the snap of falling trunks. Over it all rise the voices of animals. Hoarse bellows of hadrosaurs, the sharp, panicked cries of small bird-like dinosaurs, the calls of mammals, lizards, and crocodilians, all echo through the dark. Nocturnal hunters that once navigated by moon and star are suddenly blind, their celestial compass erased. Diurnal giants, forced into this unnatural night, stumble, collapse, or simply huddle together, muscles trembling from shock and exhaustion. How do you find food, water, or safety when the world has no up or down, no horizon at all? With the sun cut off, the surface begins to cool. At first, the lingering heat of fires and still warm oceans holds back the worst of the chill. But away from these vast reservoirs of energy, temperatures start to fall rapidly. Warm, humid, late Cretaceous air gives way to a sharper, drier cold. This is the opening edge of impact winter, the first hint of an era of freezing nights. Near the ground, the air itself is dangerous. Smoke, dust, and toxic gases from burning vegetation and vaporized rock mix into a harsh, choking haze. Large, active animals struggle to pull enough oxygen through clogged lungs. Each breath burns. Burrows, caves, and even shallow ponds and lakes become precious refuges, filtering the worst of the fallout for small, low-metabolism survivors that may one day inherit this changed world. And yet, as overwhelming as this feels, it is only the first of many such nights. What seems like a brief catastrophe will stretch on into months, perhaps years, of dim, cold days and nearly starless darkness. Join us as we follow that unfolding crisis and watch how it will set the stage for a new evolutionary chapter. For the first time in more than 150 million years, the age of the biggest creatures to ever walk the earth has ended in earnest. This unnatural night is not just an ending. It is the opening curtain on a world of scale we can barely imagine, a new earth waiting in the dark. The age of light has ended. Now the air itself turns against life. In the first hours of this unnatural night, Earth's atmosphere becomes a harsh experiment chamber, mixing ingredients no creature has ever breathed before. Above us hangs not a clear sky, but a churning cloak of dust, ash, and chemical fumes. What does it mean to try to survive when every breath is a gamble? All around the planet, the air is no longer simple. It is a complex suspension of shattered Earth. Fine rock dust blasted from the Chicxulub crater drifts high into the atmosphere, scattering the last traces of twilight. Sulfate aerosols form as vaporized gypsum from the Yucatan crust reacts and condenses, creating a pale, reflective haze. Black carbon from colossal wildfires rises in oily plumes, while gases like sulfur dioxide and nitrogen oxides seep into the mix. This is not the breathable air of the late Cretaceous. It is the first draft of a toxic new era. Near the Great Burn Zones, the effect is immediate and brutal. Forests that only hours ago sheltered the biggest creatures to ever walk the earth now smolder and roar, feeding dense, acrid smoke into the low atmosphere. Carbon monoxide levels spike, binding to blood and silently stealing oxygen from the bodies of any animal still moving through the gloom. Oxygen itself is not gone from the planet, but close to the ground it is effectively diluted, displaced by smoke and heated gases. Large, active dinosaurs that survived the initial blast now struggle with every step, their massive lungs pulling in air that can no longer sustain their racing hearts. Higher in the atmosphere, chemistry works on a slower, relentless clock. Sulfur dioxide and nitrogen oxides begin to react with water vapor, forming droplets of sulfuric and nitric acids. The full fury of acid rain lies days ahead, but the process has already started. Some of these acidic aerosols are small enough to ride the winds tonight, irritating eyes, burning the lining of throats, and inflaming the delicate airways of reptiles, birds, and mammals alike. Breathing becomes an act of abrasion. Yet even in this global crisis, the air is not uniform. Conditions vary from place to place, moment to moment. Over open oceans, far from the most intense fires, the low-level air may remain comparatively cleaner, despite the dust veil high above. Remote coastlines, windward slopes, and sheltered valleys can briefly escape the worst smoke, offering scattered temporary refuges. In this shattered world, survival may hinge on being in just the right pocket of air, at just the right time. Some strategies suddenly become priceless. Animals that can slow their metabolism and wait, burrowing mammals, hibernation-capable reptiles, amphibians sealed in mud, insects hidden in soil. Avoid the thickest, most poisonous layers. Creatures that can stay submerged in water for long stretches. Let the surface air pass above them like a deadly tide. Even shallow ponds and river margins become crude filters, sparing gills and lungs from the most dangerous fumes. For birds and other flying survivors, the sky is both escape route and trap. Mobility allows them to leave burning forests and seek distant shores, but every wing beat carries them through ash, soot, and swirling particulates. Disorienting darkness hides landmarks. Volcanic-like aerosols sting their eyes and clog their air sacs. Some will find new havens. Many will simply exhaust themselves in toxic twilight. Layer by layer, the stressors accumulate. Heat from re-entering ejecta, shock from earthquakes and tsunamis, fire racing across continents, smoke thickening the air, and now an atmosphere chemically primed to corrode living tissue. This extinction is not the work of a single blow, but of cascading pressures that leave almost no refuge untouched. Above the choking ground-level haze, another threat is quietly assembling. As sulfur and nitrogen compounds continue to mingle with water vapor, clouds rich in acid begin to form in the dark. Join us as we follow those forming storms and watch how, in the coming days, corrosive rains will fall on an already broken Earth, washing this ancient world into a new and harsher chapter. Those clouds are not just dark, they are loaded. In the hours after impact, the sky above this broken Earth becomes a chemical factory, quietly preparing a new kind of storm. When the asteroid struck the Yucatan, it did more than shatter rock. It vaporized thick layers of sulfate-rich sediments, blasting colossal quantities of sulfur dioxide high into the atmosphere. At the same time, the air itself was torn apart. The superheated shock front split nitrogen and oxygen molecules, forging reactive nitrogen oxides. As these gases spread around the ancient world, they met something else, still rising from oceans and burning forests. Water vapor. In that turbulent mixture, simple reactions begin to set the stage for a different kind of rain. Sulfur dioxide dissolves into tiny droplets and oxidizes, forming sulfuric acid. Nitrogen oxides react with water to produce nitric acid. At first, these acids are suspended in the roiling clouds, carried by fierce winds through the global night. But as the upper atmosphere starts to cool, towering convective storms boil upward, and those microscopic acid particles become the nuclei of raindrops. Now the sky can finally let go. As the first organized storm bands sweep across continents, they scour the air, collecting these acids into liquid form. The result is precipitation far more acidic than any normal rainstorm, falling on landscapes already scorched and choked with ash. In some regions, especially downwind of the impact in volcanic provinces, the first corrosive showers begin before the night is over. In others, they arrive with the dim, ash-filtered dawn. Imagine an exposed dinosaur relative that somehow survived the firestorms, or a mammal emerging from its burrow to drink. Raindrops that would once have cooled hot skin now sting eyes and inflamed nasal passages. Leaves already wilted by heat and darkness begin to lose vital nutrients as the acidic water strips away calcium, magnesium, and potassium. Forest canopies, grasslands, and fern thickets are chemically weathered from above, their soils leached and weakened just when plants most need every reserve. Freshwater systems are hit even harder. Small lakes, ponds, and thin streams have little buffering capacity, so their pH can plunge quickly. Sensitive fish suffocate as acid damages their gills. Amphibian eggs and larvae, already stressed by ash and falling temperatures, fail to develop. Microscopic plankton, the base of many food webs, die off in pulses. What happens to the giants of an ecosystem when its tiniest foundations collapse? The oceans fare slightly better, but not unscathed. Their sheer volume and dissolved minerals act as a massive chemical cushion, preventing a uniform, catastrophic drop in pH. Yet surface waters and enclosed coastal basins, especially near river mouths delivering acidified runoff, experience dangerous shifts. Coral-like organisms, shell builders, and planktonic communities are pushed to their limits. Acid rain is not the single executioner of this extinction. It is one more blow, layered on top of darkness, cooling, wildfires, tsunamis, and habitat loss. Climate models and geochemical signatures in clay layers enriched with sulfur and altered isotopes point to a sharp pulse of acid deposition after the impact, though its exact intensity and duration remain debated. Was it a brief, brutal deluge or a longer grinding assault? Either way, by the time these corrosive storms begin to ease, the rules of survival have changed. With the sky darkened, temperatures falling, and ecosystems chemically and physically battered, which forms of life are best positioned to endure the long, cold aftermath that has just begun, and which will vanish forever from a world of scale we can barely imagine? But while the sky burns and the rains turn sour, something deeper is happening that no eye can see. The entire planet shudders. For a brief, terrifying moment, Earth itself behaves less like solid rock and more like a struck bell. The Chicxulub impact releases seismic energy equivalent to a magnitude 10 or even 11 earthquake, far beyond anything in human records. The largest quakes we know barely reach magnitude 9.5. This is not just a big earthquake, it is a planetary-scale jolt. Energy slams into the crust and mantle, compressing, shearing, and flexing the deep interior. From that single point on the Yucatan margin, waves of distortion race outward in all directions, through continents, beneath oceans, along ancient fault zones laid down long before the biggest creatures to ever walk the Earth evolved. First come the P waves, the primary or pressure waves, squeezing and stretching rock as they travel. They move fastest, crossing whole oceans in minutes, making distant ground thump like the passing of some colossal underground engine. Close behind are the S waves, the shear waves, shaking material side to side, unable to pass through liquid, but roaring through solid crust and mantle. Finally wrapping the globe are the surface waves, rolling and heaving the ground itself. These are the waves that topple forests, tear open fissures, and turn stable slopes into avalanches. Within tens of minutes, regions on the far side of the planet feel the impact. River valleys in what will one day be Asia and Europe convulse. Cliff faces crumble into foaming seas. Coastal shelves fail in sudden, catastrophic slumps. Where sediments are waterlogged, the shaking forces grains apart and drives water upward. Whole stretches of delta plain liquefy, behaving more like thick mud than solid land. Imagine standing on familiar ground and feeling it flow around your feet. How do animals react when the very definition of solid Earth disappears beneath them? As these seismic waves circle the globe, they do not just damage the surface, they rearrange it. River channels are abruptly rerouted as banks collapse and beds are uplifted or dropped. Deltas at the margins of ancient inland seas sag and slide. Vast packages of sediment plunging into deeper water. Each submarine landslide displaces enormous volumes of seawater, sending out secondary tsunamis thousands of kilometers from Chicxulub. Join us as we follow these hidden cascades of cause and effect, where one impact sets the stage for countless local disasters. For life already reeling from firestorms and toxic downpour, this shaking is a final insult. Burrow systems that might have offered shelter collapse, suffocating small mammals, lizards, and invertebrates, or sealing them in darkness. Nesting sites on riverbanks and coastal bluffs slump into churning water. Eggs and hatchlings swept away. Forest floors fracture. Root systems tear. Animals that navigate by subtle ground vibrations or stable landmarks find a world that is literally moving under them. How do you flee when every direction pitches and heaves? In this first hour, evolution's careful architecture of habitats is smashed and smeared. Ancient shorelines vanish, replaced by raw scarps and unstable slopes. The Mesozoic Earth is being redrawn in real time, line by trembling line, and as the seismic ringing slowly fades, another force begins to dominate the night. The restless, rising oceans driven into motion by all this sudden change. those restless oceans do not just heave, they rise up as walls. When the asteroid slams into the shallow tropical sea of the Proto-Gulf of Mexico, it does not simply make a splash. It excavates a transient crater more than 100 kilometers wide, scooping out cubic kilometers of water and seafloor in a fraction of a second. Rock, vapor, and seawater are blasted skyward. Around the rim of this collapsing cavity, displaced water surges back, stacking into a ring of waves hundreds of meters high. Not storm waves, moving cliffs. In that first minute, the sea near ground zero is unrecognizable. Where there was once a warm, sunlit shelf teeming with ammonites, corals, and the biggest creatures to ever walk the earth along nearby coasts, there is now a plunging void. As the crater walls slump and rebound, pulses of energy race outward through the water. Join us as we follow those pulses as they unfurl into megatsunamis, the first planetary-scale response of Earth's oceans to this sudden wound. From the impact site, waves radiate like shock rings, racing across the Proto-Gulf of Mexico at jet airliner speeds. They pour into the Western Interior Seaway, the vast inland ocean that once split North America in two, and out into the young Atlantic. As they travel thousands of kilometers, their towering crests slowly spread and lower, but they remain immense, tens of meters high in deep water, still more than enough to reshape entire coastlines. Can we imagine standing on a Cretaceous beach as the horizon itself begins to rise? Landfall turns abstraction into annihilation. When these walls of water hit coastal plains, they do not gently flood. They strike like moving mountains. Forests are ripped out by the roots, trunks snapped and carried like battering rams. Coastal wetlands and dinosaur nesting grounds are scoured clean down to bedrock. Marine reptiles, fish, and invertebrates are swept inland together with hadrosaurs and horned dinosaurs, tumbled into churning, debris-laden torrents. In a world of scale we can barely imagine, even colossal animals are tossed like driftwood. The waves surge far beyond the normal reach of tides, racing up river valleys and low-lying basins, then retreating in violent backwash that drags sediments and carcasses seaward again. Each advance and retreat lays down a chaotic signature, mixed layers of sand, mud, broken shells, and shattered plant material. These are not quiet burial grounds. They are the frozen record of minutes of terror. Today, we can still read those minutes in stone. Along the margins of the ancient Western Interior Seaway, geologists find tsunami deposits where marine and terrestrial sediments are jumbled together, and boulder-sized clasts have been hurled far inland by water that should never have reached them. Similar disturbed layers appear as far away as the Caribbean and even the Atlantic, testifying to the global reach of these waves. They set the stage for coastlines that are abruptly redrawn, habitats erased, and ecosystems forced into instant crisis. But as the oceans fall back and the night deepens, another darker tide is rising in the sky above. What happens when the very air of the planet turns against life? As the tsunamis race back toward the sea and the reshaped coastlines fall briefly silent, the true enemy of this first night gathers overhead. The oceans have surged and retreated, but now the sky itself is about to burn. For a few hours, Earth is transformed into a kind of upside-down furnace, with the heat coming not from below, but from above. When the asteroid struck, it did not just excavate a crater. It blasted the crust and shallow ocean into space as ejecta, a churning mix of rock vapor, molten droplets, and fine dust. Some of this material arced out on ballistic trajectories like artillery shells on a planetary scale. Some fragments and vapor plumes were hurled so high, they briefly skimmed the edge of space, even looping into temporary orbit before gravity called them back. These droplets would cool into glassy beads we call tektites, tiny time capsules of that single catastrophic moment. As this colossal veil of debris begins to fall, it does not drift gently. It plummets at many kilometers per second, turning the atmosphere itself into a breaking layer. Each grain, each droplet, each fragment becomes a tiny projectile, compressing and heating the air in front of it. Imagine not a few blazing meteors, but trillions of them, sweeping around the planet in overlapping waves. The upper atmosphere glows, first like a sunset that will not end, then like the heating element of a global broiler drawn across the sky. From the surface, the effect is not a rain of individual fireballs, so much as a continuous, searing radiance. The superheated air high above re-emits its energy downward as intense infrared radiation. In many regions, that thermal pulse is strong enough to ignite dry vegetation directly, even without a single spark touching the ground. Leaves shrivel, resin boils, and forests that stood for millions of years burst into flame almost at once. For the biggest creatures to ever walk the earth, there is nowhere truly safe in the open. Exposed animals are scorched where they stand, their skin and eyes overwhelmed by the radiant heat. Small, burrowing mammals and sheltering reptiles retreat deeper into soil and crevices, where even a few tens of centimeters of earth can mean the difference between life and instant death. We step back hundreds of millions of years in our minds, yet the physics is the same as in a modern blast furnace, simply scaled to a whole planet. Yet this global broiler is not perfectly uniform. Some regions are shielded by thick clouds of dust, or water vapor, or impact-generated storm systems that absorb and scatter part of the radiation. Deep valleys, shadowed canyon walls, and the undersides of dense fern thickets experience a less brutal pulse. Over open oceans and large lakes, the water surface absorbs and redistributes heat, sparing life in the depths, even as shorelines blaze. These patchy refuges, scattered across a largely burning world, set the stage for which lineages will thread the needle of extinction, and which will vanish forever. As the flames spread, and the sky gradually darkens with smoke and dust, another transformation is coming. What happens when the fires give way not to recovery, but to a long, lethal winter? The fires do not stay local. They race outward. What began as scattered ignition points beneath a superheated sky merges into something far more terrifying: a planet wrapped in flame. Before humans, before cities, before history itself, this ancient world belonged to giants. Not just the biggest creatures to ever walk the earth, but entire forests that had grown undisturbed for millions of years. Now, in a single catastrophic day, those conifer forests, fern prairies, and mangrove swamps become fuel. A thermal pulse from re-entering ejecta sweeps around the globe, heating the upper atmosphere to hundreds of degrees. Dry needles flash into fire. Peat-rich soils smolder. Even moist coastal thickets erupt as lightning storms, triggered by ash-charged clouds, stab repeatedly into a landscape already primed to burn. We can picture it as a continuous, advancing front. Wall-high flames roar through Cretaceous pine stands, sending columns of fire hundreds of meters into the air. Fern meadows that once cushioned the steps of colossal herbivores ignite like paper, while mangrove tangles along shallow inland seas hiss and explode as trapped gases burst from the wood. Join us as we follow these firestorms across continents, leaping rivers, climbing slopes, and circling entire basins until night itself seems to glow red. As this biomass burns, the atmosphere changes hour by hour. Soot, ash, and microscopic charcoal swirl upward in thermals that tower higher than modern thunderheads. Each burning valley adds its plume. Each forested ridge contributes another black column. Together, they inject vast quantities of carbon-rich particles and aerosols into the sky, darkening it even where flames have not yet arrived. What was already a dust and sulfate-laden shroud from the impact now thickens into a layered cloak of grit and smoke. The sun dims. Shadows blur. In many regions, day turns to a copper twilight long before true night falls. The ecological consequences are immediate and brutal. Canopy cover that once moderated temperature, sheltered nests, and fed browsers is stripped away in days. Nesting sites in tree hollows, on branch platforms, and in low undergrowth are incinerated. Eggs cook in the heat or are buried under falling charcoal. For large herbivores that survived the initial blast, the world they knew disappears almost overnight. No broad-leaved branches to strip, no seed-laden cones to pluck, no fern fronds to sweep into massive jaws. How do you move a body built for abundance into a landscape of ash? We know this is not just speculation, because the rocks remember. At the boundary between the Cretaceous and the Paleogene, geologists find thin but global layers rich in soot, microscopic charcoal, and burned plant fragments. In some sites, up to half of the organic particles are charcoal, a silent census of forests that burned almost everywhere. These blackened horizons, sandwiched between older, thriving fossil soils and the impoverished post-impact layers, set the stage for a long, lethal winter. But what happens to a biosphere when the flames finally die and the smoke itself becomes the next killer? When the last crowns of flame dimmed on the horizon, the sky did not clear. It changed. Instead of open stars above the ruined continents, a new storm assembled overhead, built not from water, but from rock turned to vapor and glass. In the first instant of impact, crustal rocks and sediments were blasted into a superheated plume, rising higher than any thunderhead, punching through the atmosphere and briefly brushing space itself. As that colossal column expanded and cooled, droplets condensed out of the rock vapor. Not raindrops, but molten beads of silicate glass. These are tektites and microtektites, tiny projectiles born in a fraction of a second, then flung around the entire Earth. Imagine a global sprinkling of glassy hail, grains no larger than sand or as big as pebbles, arcing through the darkness and beginning their long fall back toward the shattered surface. As they raced through the air, many of these droplets rounded into perfect spheres, their surfaces smoothed by friction and rapid cooling. We call these spherules. Mixed among them were fragments of minerals that had been shocked by pressures far beyond ordinary volcanoes or earthquakes. Quartz, a common, durable mineral in continental crust, had its internal crystal lattice twisted into rare structures that only form under extreme shock. These shocked minerals, together with the glassy tektites, are the diagnostic fingerprints of a single, catastrophic impact, a geological signature that no slow, gradual process can counterfeit. Join us as we follow these particles through the first hours and days after the blast. Before humans, before cities, before history itself, this rain of glass fell silently into oceans and onto burning forests. Some spherules vaporized in midair, adding yet more dust. Others splashed into the sea, settling like strange snow on coral reefs and coastal plains. Layer upon layer of ash, soot, microtektites, and shocked grains filtered down through the choked atmosphere, forming a thin but truly global horizon. This is the KPG boundary, a line often no thicker than a finger, yet rich in iridium and other extraterrestrial markers that betray the asteroid's origin. What did this ashfall mean for life that had survived the first shock and firestorm? Fish and ammonites drew water thick with fine particles across their gills until the delicate filaments clogged and failed. On land, leaves were quickly coated with dust and glassy grit, their sun-catching surfaces dulled. Photosynthesis strangled even before the sky went fully dark. Small animals, from mammals to lizards and birds, inhaled abrasive air that scoured lungs and throats. Every breath became work, every hiding place filled with powder. This was not just a geological bookmark, it was a weapon. The same layer that allows us to step back hundreds of millions of years in our imagination and pinpoint the day the biggest creatures to ever walk the earth met their fate. is also the record of a suffocating world. Yet even as this planet-dusting storm settled, another change was building above the clouds, one that would plunge Earth into a world of scale we can barely imagine: a long, global night. How does a biosphere endure when day itself disappears? That long global night does not fall all at once. It begins with a dimming so subtle that, for a moment, the ruined Earth almost seems to exhale. The blinding, white-hot glare of re-entering debris fades. The rain of molten glass slackens, and the sky that was a furnace begins to change into something else entirely. Above the smoke of burning forests and churning seas, a second, higher veil is forming. Dust from pulverized rock, droplets of sulfate from vaporized sulfur-rich crust, and fine black soot from worldwide wildfires rise and spread into the upper atmosphere. There, tens of kilometers above the surface, they start to do something deceptively simple, but globally decisive. They interfere with sunlight. This is radiative forcing in its most violent form. Particles high in the air reflect some of the sun's energy back into space and absorb more of it themselves, so that far less light and heat ever reach the ground below. At first, in the hours after impact, the sky still glows. Not a gentle blue, but a dull metallic brightness, as if the whole dome above you were made of embers and ash. Then, as the expanding plume wraps around the planet, that brightness thickens into haze. Midday begins to look like a storm at dusk. Shadows blur and lengthen. The sun, when you can see it at all, is no longer a blinding disk, but a dim, reddish coin, smeared behind layers of dust, or swallowed completely by the spreading shroud. Before humans, before cities, before history itself, light itself is being stripped from the surface. Not just a cloudy day, but the systematic shutting down of the main energy source that drives winds, weather, and life. Join us as we follow those first critical hours when radiative forcing turns from an abstract concept into a planetary sentence. As more soot from distant fires is lofted into the stratosphere, the haze grows darker and more uniform, stretching from horizon to horizon like a solid ceiling. At ground level, the change is immediate and unnerving. Even while trees still burn and impact-triggered wildfires race across continents, the air above them starts to cool. With sunlight cut off, surfaces that were seared earlier in the day begin to lose heat to the overlying air and then to space. In some regions, temperatures may drop by tens of degrees within a day. Imagine standing in a devastated Cretaceous forest, feeling the heat of nearby flames on your face, while a chill wind slides in from a darkening sky. How long can ecosystems built for a warm, stable Mesozoic era endure such a reversal? These first shadows set the stage for what scientists call an impact winter, a prolonged period of global darkness and cold, driven by that altered balance of incoming and outgoing radiation. Step back hundreds of millions of years in your mind, and you can see this as the opposite of the lush greenhouse climates that once allowed the biggest creatures to ever walk the earth to thrive. Now, instead of warmth and light feeding forests of conifers and flowering plants, we have a world of scale we can barely imagine, where photosynthesis falters, food chains fracture, and survival hinges on a single question. Which life forms are built to withstand a long, freezing night that has only just begun? But cold and darkness are only part of this new nightmare. The sky itself is turning poisonous. When the asteroid slammed into what is now the Yucatan, it did not just hit rock. It tore into thick layers of sulfur-rich carbonates, ancient seafloor sediments packed with gypsum and limestone. In a fraction of a second, those layers were flash vaporized, their sulfur ripped apart and hurled upward as massive plumes of sulfur dioxide gas. At the same time, forests and coastal swamps across the Cretaceous world are burning, feeding the air with smoke, carbon dioxide, and a haze of organic compounds. Above the firestorms, re-entering ejecta and lightning bolts rip through the choking atmosphere, forging nitrogen oxides from the very air itself. Before humans, before cities, before history itself, this was chemistry on a planetary scale. Not just a polluted sky, but a reactive cauldron. As the hot, dust-laden atmosphere cools, water vapor condenses around these new gases. Sulfur dioxide reacts with oxygen and water to form tiny droplets of sulfuric acid. Nitrogen oxides combine with moisture to make nitric acid. Within days, high-altitude winds spread these corrosive aerosols around the globe, building belts of acidic cloud that circle Earth like ghostly, stinging shrouds. Soon, the first rains fall. They are not gentle. They are not life-giving. Raindrops carry dissolved sulfuric and nitric acids, driving the pH of surface waters sharply downward. In some regions, the rain may be as acidic as the contents of a modern car battery. Leaves that survived the initial blast now blister and blacken as the droplets land, their tissues chemically burned. Needles of conifers turn brown from the tips inward. On the forest floor, this same rain leaches vital nutrients from the soil, stripping away calcium and magnesium, releasing pulses of aluminum that are toxic to many roots. In lakes, rivers, and coastal seas, the impact is just as brutal. Fish and amphibians feel the burn directly on their skin and gills. Eggs lying in shallow water are bathed in acid they were never built to endure. Plankton at the base of marine food webs struggle as surface waters shift from supportive to corrosive. We watch, in this first long night, as already stressed ecosystems face yet another invisible assault. How many species can survive fire from above, freezing air, and now chemical attack from the clouds? These acidic rains do more than kill. They also reshape the geology of the recovering planet. As they flow over fresh impact debris and exposed bedrock, they accelerate chemical weathering, dissolving minerals and carrying floods of dissolved metals and ions into streams and oceans. Iron, manganese, and other elements surge through watersheds, briefly enriching some environments while poisoning others. Join us as we follow these chemical pulses forward in time to see how they set the stage for a different kind of world after the extinction, and to ask one more unsettling question. What happens when the oceans themselves begin to change? Those rivers of metal and ash do not just reshape the continents. They surge into the seas, and the oceans answer with violence. Before the first true night after impact, the surface of the ancient world's waters has already begun to tear itself apart. The asteroid strikes in a shallow sea, and the basin itself becomes a weapon. Walls of water rise hundreds of meters high, then race outward as colossal tsunamis. Not just big waves, but moving cliffs of ocean. As they cross basins and slam into continental shelves, they drag warm surface waters down and heave cold, nutrient-rich deep waters up, shredding the stable layers that many marine organisms depend on. Creatures adapted to narrow temperature bands, from delicate plankton to reef-building invertebrates, are suddenly thrust into a chaotic mix of hot and cold, fresh and salty, light and dark. At the same time, seismic waves from the impact rattle the seafloor. Submarine landslides roar down continental slopes, stirring sediments into thick, choking clouds. Previously clear waters turn into underwater dust storms. Filter feeders that once thrived in calm, stratified seas now face an abrasive blizzard of particles. This frantic mixing briefly floods surface waters with nutrients, but it also sets the stage for something far more deadly in the hours and days to come. Above, the atmosphere fills with carbon dioxide, sulfur, and nitrogen compounds. As the first pulses of acid rain strike the ocean's skin, they dissolve rapidly into the surface layer. The chemistry of the water shifts in minutes. pH drops. Carbonate ions, the building blocks of calcium carbonate, become scarce. For organisms that build shells and skeletons from this mineral, ammonites spiraling through the midwaters, tiny coccolithophores and foraminifera drifting near the surface. This is an invisible catastrophe. Shells begin to thin and dissolve. New growth becomes harder, then impossible. How do you survive in a sea that is quietly erasing your body from the outside in? The biological response is just as abrupt. Shocked by temperature swings, poisoned by changing chemistry, and battered by sediments, vast numbers of plankton, invertebrates, and fish die and sink. Their bodies rain down onto the seafloor and into midwater layers. Bacteria feast on this sudden flood of organic matter, consuming oxygen faster than it can be resupplied by a circulation system already scrambled by tsunamis and turbulence. Pockets of low oxygen bloom into spreading dead zones. In these suffocating regions, fish gasp at the limits of their gills and fail. Crustaceans stagger, then fall still. Even large marine reptiles, already stressed by the shockwaves and collapsing food supplies, find fewer and fewer safe refuges. The oceans, once home to giants that rivaled the biggest creatures to ever walk the earth, begin to fall silent from the bottom up. Yet the most fragile link is also the smallest. Photosynthetic plankton at the sunlit surface form the base of nearly every marine food web. As dust, soot, and aerosols from global wildfires spread, the bright Cretaceous sky dims toward a permanent twilight. Light levels drop hour by hour. With less sunlight, plankton photosynthesis slows, then stalls. Energy entering the marine system contracts. We see, in these first hours, the outline of a catastrophe that will unfold over weeks and months. Fewer plankton mean less food for small grazers, which means starvation for larger predators, from fish to mosasaurs. Join us as we follow this unraveling and ask one more haunting question. When darkness deepens and the seas themselves turn hostile, who, if anyone, can still find a way to endure? But while the oceans begin to unravel, the land itself is already a battlefield, and at its center stand the giants. Before humans, before cities, before history itself, the Earth belonged to colossal land animals that ruled entire continents, not just big predators and herbivores, but the biggest creatures to ever walk the Earth, now facing a first day unlike any other in the history of life. In a North American valley, a Tyrannosaurus rex lumbers through choking dust. This is an apex hunter built for abundance, for tracking herds of hadrosaurs and horned dinosaurs across vast territories. She needs hundreds of kilograms of meat every week, a constant flow of living biomass to fuel her massive frame. Today, the forest around her is burning. Fire fronts, kindled by falling molten debris, race along ridges and down into lowlands. The air is thick, hot, and heavy with ash. She can run, but she cannot hide underground, cannot squeeze into a burrow or a rock crevice. Where does a 7-ton predator find clean air when every direction glows orange? On the floodplains, her usual prey are in chaos. Triceratops herds, animals as long as a bus and armored with horns and frills, were adapted to roam broad river valleys, cropping endless carpets of ferns and flowering plants. Their size once meant safety in numbers and defense against any single attacker. Now it becomes a trap. As fires close in and embers rain down, these giants cannot simply dart through dense forest or climb steep ravines. Their own bulk slows them at the very moment speed and agility mean survival. Further south, on Cretaceous coastlines and inland plains, titanosaurs dominate the horizon. These sauropod giants, some over 30 meters long, were living engines of plant consumption, their long necks sweeping through trees the way a scythe passes through grain. They depended on stable climates and predictable wet seasons to grow forests fast enough to keep up with their feeding. In the first day after impact, shockwaves trigger landslides and mega tsunamis surge far inland. Herds of titanosaurs are caught in receding waters or on collapsing riverbanks, their pillar-like legs no match for churning debris-laden floods. Even those that survive the waves face a sky that darkens by the hour. Physiology, which once set the stage for their success, now turns against them. Large bodies store heat. They cool slowly. As the atmosphere near the ground becomes an oven from re-entering ejecta, low-lying areas fill with superheated, smoky air. Smaller animals can retreat into burrows, cracks, or deep water, or shelter beneath rocks and fallen logs where temperatures are slightly lower. A titanosaur's chest, held just meters above the ground, is forced to inhale that lethal mix with every breath. These giants also share another vulnerability. They reproduce slowly, with long generations and relatively few offspring compared to their size. Even if some individuals endure the first night, any sharp drop in food or nesting sites will echo through their populations for decades. Contrast that with small mammals, lizards, and the bird-line dinosaurs that can lay many eggs, mature quickly, and exploit scraps of food in devastated landscapes. In a world suddenly hostile to giants, being small and adaptable is no longer a compromise. It is a decisive advantage. As darkness deepens and the first day closes, we begin to see a brutal pattern. The very traits that define dinosaur grandeur now magnify their risk. Join us as we follow the survivors into the long, cold nights ahead and ask, when the fires fade and the true impact winter begins, which lineages can cross that abyss and which will vanish into the fossil record forever? In that brutal pattern, one truth begins to stand out. Size is no longer safety. Now survival belongs to the small, the hidden, and the already cautious. As the sky turns from daylight to a sheet of burning re-entry fire, early mammals retreat from the open world they have always feared. They rush down pre-dug burrows, squeeze into root tangles, and vanish into rock crevices as the first incandescent ejecta streak overhead. A few meters of soil or stone become a massive shield, blocking the radiant heat from a sky briefly heated to oven-like temperatures and catching the hail of glassy droplets before they can sear flesh. These are not heroic new behaviors. They are the same nocturnal habits that kept them out of sight of the biggest creatures to ever walk the earth. They are not alone underground. Small lizards, already used to wedging themselves into cracks to escape the midday sun, press deeper into the cool dark. Snakes coil in abandoned mammal tunnels. Amphibians back into moist burrows and muddy refuges, their thin skins protected by layers of damp earth. Even invertebrates, from beetle larvae to burrowing insects and worms, simply do what they always do: remain below the surface, insulated from the worst thermal pulse and the first shock of falling debris. In a world where colossal bodies are exposed on open plains, these minor players are suddenly holding the best cards. Water too becomes a refuge. Shallow ponds, lakes, and slow rivers absorb and disperse heat, turning what would be a lethal blast in air into a more muted surge. Fish dive deeper into the dim, cooler layers. Turtles hunker into the soft bottoms of ponds or lurk beneath overhanging banks, shells and water together, forming a double barrier. Crocodilians slip below the surface, nostrils barely raised, riding out the chaos as waves of pressure and light ripple overhead. In these basins and channels, the first night after impact feels different. Not safe, but survivable. Join us as we follow this quiet exodus into shelter and see how behaviors that evolved for ordinary droughts, predators, and seasonal extremes suddenly set the stage for endurance in an extinction-level event. Before humans, before cities, before history itself, these strategies were being tested in the harshest laboratory Earth had ever seen. Was it luck that so many survivors were small? Or was it the slow, steady evolution of hiding, digging, and diving that prepared them for this single catastrophic day? As true darkness finally closes over the fires, a planetary survival lottery is underway. In burrows, in mud, beneath ice-heated waters, countless eyes remain shut, waiting. When they open again, whose footsteps, whose wing beats, whose quiet rustles will shape the next era, and which hidden lineages will emerge to inherit a world of scale we can barely imagine? In that darkness, as the last embers fade and the ash begins to settle, not every dinosaur voice is silenced. Some are only reduced to whispers. We tend to imagine the extinction as a clean break, a single terrible night that erases an entire kind of animal. Yet high above the scorched ground, clinging to branches, huddled in reeds, the avian line of dinosaurs is fighting for breath. Birds are not just relatives of dinosaurs. Birds are dinosaurs. They are the only branch of the theropod family tree still alive. But even here, the catastrophe is ruthless. The late Cretaceous sky had been crowded with diversity. Toothed seabirds slicing over waves, strange winged forms like Hesper ornithiforms diving after fish, early relatives of modern birds flitting through forests. Most of these lineages will vanish into the dark. Only a few small ground-living groups will step across the boundary into the next era. What separates the survivors from the lost? Body size is one brutal filter. When firestorms sweep continents and fresh leaves wither in the impact winter, massive, specialized forms are trapped by their own needs. Smaller birds can eat less, hide more easily, and endure longer gaps between meals. A sparrow-sized dinosaur can shelter in a crevice or beneath dense undergrowth in a way a vulture-sized one never could. On this night, being little is a colossal advantage. Mobility matters as well. The ability to fly, or at least to sprint and flutter from one refuge to another, lets some birds escape the worst heat pulses and falling debris. As ejecta rains down and forests ignite, they can drop into river margins, wetlands, and lakeside thickets, then move again as each temporary haven becomes unsafe. Join us as we follow them into these narrow pockets of survival. Tangled roots along a muddy bank, reed beds steaming under a sky that glows dull red, half-collapsed forest floors where fallen trunks still offer shade. Diet may be the most decisive trait of all. Many of the doomed bird groups depended on live fish, fresh foliage, or rich marine ecosystems that are collapsing by the hour. The lineages that endure are likely those with flexible, almost indiscriminate appetites. They peck at seeds buried in the soil, at insects stunned by heat, at carcass scraps and detritus washed into channels. Seeds in particular are tiny time capsules of energy, able to survive fire and frost. Birds that can crack, grind, and swallow them can bridge the long, hungry months of darkness. From these few adaptable survivors, the future will unfold. The ancestors of modern waterfowl cling to life along blackened shorelines. Proto-game birds scratch in the ash for anything edible. Early branches that will one day give rise to songbirds endure in the gloom, their calls muted, but not erased. When light finally returns, the forest will not resound with the bellows of the biggest creatures to ever walk the earth, but with these smaller voices, descendants of that first night's refugees. In the silence left by the fallen giants, whose footsteps will answer those new songs, and what forms will evolution sculpt from the shadows they leave behind. But while the forests fall silent and the songs of small survivors begin to rise, another refuge waits where land meets water. Along riverbanks, in coastal swamps, in the tangled margins of ancient lagoons, life has one more shield to raise against the worst night in 4.5 billion years. Here, at the water's edge, some of the most resilient reptiles on Earth slip beneath a liquid barrier. As fires race through Cretaceous wetlands, flames reflecting in sheets of drifting ash, crocodiles slide from collapsing banks into murky channels. One powerful kick, then stillness. They sink below the surface, eyes and nostrils vanishing under a film of soot and floating debris. For minutes, then hours, they can remain submerged and nearly motionless, hearts slowing, muscles quiet, letting hot winds and burning embers scour only the air above. When the sky rains molten glass and charcoal, the water absorbs the heat, blunting the lethal temperature spike that roasts exposed animals on land. These are not the biggest creatures to ever walk the Earth, but they are specialists in endurance. Their bodies, low and armored, hug the bottom where temperatures shift more slowly than in the air. Buried in cool mud or pressed into underwater ledges, they ride out shockwaves, falling branches, and waves of scalding steam. Join us as we follow them through this first night, not as hunters, but as patient fugitives from a world on fire. Turtles share this borderland between land and water, and their defenses are layered. Many species already dig deep burrows to lay eggs, carving nests into riverbanks, floodplain sands, or forest soils. In the chaos after impact, those same instincts become life-saving strategies. Adults can push themselves into wet sediment, half buried in mud at the bottoms of ponds and lakes, while juveniles retreat under logs, into crevices, or entirely within their shells. A shell is not just armor against teeth. It is a buffer against sudden cold, falling ejecta, and searing ash. As the impact winter begins and temperatures plunge, ectothermic metabolisms become an unexpected advantage. Crocodiles and turtles, fueled by the sun in normal times, can dial their energy use down to a fraction of a warm-blooded animal's needs. Where a small dinosaur or bird must eat frequently to maintain a high internal temperature, these reptiles can fast for weeks or months, surviving on stored energy while food webs above them collapse. In a period when photosynthesis falters and plant growth nearly stops, low energy demands mean the difference between endurance and extinction. Fossil evidence confirms this quiet resilience. Across the KPG boundary, crocodilians and many turtle lineages show comparatively low extinction rates, even as colossal dinosaurs vanish from the record. Their continued presence set the stage for new ecosystems along rivers and coasts, anchoring food chains in a world of scale we can barely imagine reshaping itself from the bottom up. Yet even here, sheltered by water and mud, how long can these survivors endure a planet darkened for months, perhaps years, on end? Yet even as the surface freezes and the skies dim, another story is beginning in the shadows. While colossal bodies lie where they fell, it is the small, the hidden, and the easily overlooked that move first across this altered Earth. Before humans, before cities, before history itself, the world belonged to giants. Not just the biggest creatures to ever walk the Earth, but forests that stretched for continents and ecosystems layered from canopy to soil. Now, as those forests burn, topple, and die, an entirely different kind of army is mobilizing. Insects with short lives and fast generations are suddenly surrounded by resources: dead wood, fallen fronds, and carcasses still warm beneath settling ash. Many of these insects are pre-adapted to catastrophe. They breed quickly, lay massive numbers of eggs, and can shift from one food source to another in a single generation. Beetles that once bored into living trees now tunnel through charred trunks. Termites and their relatives explore the labyrinth of collapsed roots and buried logs. Detritus-feeding larvae sift through nutrient-rich ash, turning a layer of destruction into a rough, unstable soil. In a period when large herbivores and predators are disappearing, these small invertebrates can double, then double again, exploiting a banquet created by extinction. Alongside them, and often inside the same rotting wood and bone, fungi begin their silent expansion. Fungi are the primary decomposers of this ancient world, the organisms capable of breaking down tough plant tissues, complex carbohydrates, and even the collagen and keratin of animal remains. In the geological record, scientists see a distinct fungal spike right at the KPG boundary, a surge in fossilized fungal spores that signals a post-impact boom. It is as if the planet briefly becomes a global compost heap, and the fungi rise to meet it. Join us as we follow these networks of threads and filaments spreading through the dark. mycelial webs invade buried leaf litter and skeletal remains, secreting enzymes, unlocking carbon, nitrogen, and phosphorus from what only hours ago were living dinosaurs, towering trees, and thriving reefs. What looks like decay is, in biochemical terms, recycling on a colossal scale. Every molecule they liberate has the potential one day to be drawn into a new leaf, a new root, a new body. Together, insects, fungi, and other decomposers set the stage for recovery even as the age of giants ends. They keep nutrients circulating instead of locking them away in frozen carcasses and buried forests. Without them, the impact winter ahead would not just be dark and cold, it would be chemically starved in the months and years to come as temperatures plunge and sunlight nearly disappears. Could these least charismatic survivors be the ones preventing total ecological collapse? And in that prolonged night, what other hidden strategies will life unveil to endure a world of scale we can barely imagine turned almost completely off? By the time the last curtains of ejecta have fallen, the age of dinosaurs is already ending. Yet the true horror is only now beginning. Day does not simply turn to night. It is strangled into something in between. Above the ruined continents, the dim, smoke-filtered daylight that survived the first hours thins out, not into a sunset of colors, but into a smothered, metallic gray. As the sun sinks, its disk is no longer a blazing circle. It is a faint, rust-colored bruise behind veils of dust and soot. Hurled into the stratosphere. Minute by minute, that bruise fades. Not because Earth has turned away, but because the sky itself has become an absorbing blanket, trapping heat yet blocking light. When darkness finally settles, it is not the familiar darkness of a clear Cretaceous night. It is an artificial twilight, so dense that even the brightest stars are muted, their usual pattern swallowed by the high-altitude haze. Where then does any light come from? From fire. On distant horizons, low, sullen glows mark continents where forests still burn, where cities of trees that once sheltered the biggest creatures to ever walk the earth now collapse in waves of sparks. Join us as we step back hundreds of millions of years in our minds and try to stand on one of those coastlines. The ocean that had surged inland in mega tsunamis is retreating, leaving behind tangles of uprooted conifers, broken hadrosaur bodies, and rafts of pumice and impact glass, all faintly illuminated by the orange shimmer of drifting embers. The air here is acrid and thick, loaded with smoke, dust, and droplets of acid rain. Every breath would scrape the lungs. The surf no longer roars as it did during the first catastrophic hours. It hisses, subdued as it washes over a beach newly armored with a thin layer of ash and glassy spherules. Each tiny sphere is a frozen moment of rock that was once vapor, then molten, then quenched in midair, now crunching underfoot like shattered glass. Inland, ancient forests have been reduced to smoldering skeletons. Trunks stand as blackened pillars, their crowns stripped away, their bark glowing faintly along hidden seams. The soundscape has emptied. Before humans, before cities, before history itself, these woods rang with insect calls, with the low communication of giants moving through undergrowth. Tonight, the dominant sounds are the soft crackle of embers, the occasional sighing collapse of a burning tree, and the distant rumble of aftershocks still propagating through a wounded crust. Across broad plains, this first night falls on a landscape that looks powdered. Ash lies in drifts around toppled teratopsians and scattered nests. A dusting of microtectites gives the ground a dull, glassy sparkle in the weak firelight. Shallow lakes and rivers, shocked by the thermal pulse and choked with debris, begin to lose their stored warmth. A chill seeps upward from water and soil, the first hint of the tin nearshore environments experienced corrosive conditions that added to the mounting pressure of darkness and cooling. We can still read this toxic episode in the rocks. In boundary layers at the end of the Cretaceous period, geologists find spikes in elements mobilized by intense weathering, along with signatures of altered clay minerals and sulfate deposits. These are the fingerprints of a world scoured by acid, a brief but brutal interval when the atmosphere itself turned against life. As we move deeper into this night, we will see how, beyond the chemistry of the sky, Earth's very landscapes were reshaped by the forces unleashed on that single day of impact and extinction. If the sky itself can turn against life, what does it feel like to breathe on a dying world? As the chemical fury of acid rain eases, another, more intimate threat closes in with every breath. In the hours after impact, the lower atmosphere becomes a dense, toxic soup. Forests across continents burn, releasing thick smoke and black soot that spread beneath the already darkened sky. Fine silicate dust from pulverized rock hangs in the air, each grain a tiny shard of glass. Irritant gases, ozone formed by high-energy reactions, nitrogen oxides from superheated air, mix with steam and ash. This is not the clear, humid air of the late Cretaceous. It is a choking haze that scrapes every surface it touches. When we inhale, air is meant to sustain us. Here, it betrays. Coarse particles from ash and charred debris strike the upper airways of dinosaurs, mammals, and birds, clogging nostrils and throats, triggering coughing and mucus. Finer particles behave differently. The smallest grains of silicate dust and soot slip past the larger passages, traveling deep into the lungs, lodging in the delicate exchange surfaces where oxygen should cross into blood. In creatures with bird-like lungs and air sacs, including many theropods and early birds, these fine particles infiltrate an intricate network of air channels, turning a highly efficient system into a pathway for poison. This new air does not punish all animals equally. The biggest creatures to ever walk the earth, the colossal sauropods and massive theropods that once dominated the landscape, are suddenly at a disadvantage. Their high oxygen demands and deep, powerful breaths pull more contaminated air into their bodies with every inhalation. Even far from the blast and fire zones, these giants inhale clouds of soot and dust that accumulate hour after hour. In contrast, small burrowing mammals, insect-eating lizards, and some birds that can shelter in crevices or tree hollows draw shorter, slower breaths, often through layers of soil, leaf litter, or trapped air that partially filter the worst of the fallout. Plants, rooted in place, cannot flee this invisible assault. Their leaves are coated with ash, and the microscopic pores called stomata, the gateways for gas exchange, become clogged. Acid droplets pit and scar leaf surfaces, damaging tissues that once captured sunlight with remarkable efficiency. Under a sky dimmed by smoke, the flow of carbon dioxide into leaves slows, photosynthesis falters, and the green engines that fed the giants of this era begin to stall. Behavior becomes a matter of survival. Animals that can move seek low-lying refuges, river valleys where mist and cooler air dilute the smoke, caves where stone walls block drifting ash, burrows where stale but relatively cleaner air lingers. Aquatic animals retreat deeper into lakes and rivers, using water as a temporary shield as ash and soot form greasy films on the surface. Yet even these havens are imperfect. As particulates settle, they contaminate ponds and wetlands, turning each refuge into a ticking clock. Over days and weeks, this slow suffocation transforms marginal survivors into casualties. Respiratory infections spread in weakened populations. Young animals with smaller lungs and higher metabolic needs succumb first. How many creatures perish not from fire or impact, but from the simple act of breathing in this altered world? Join us as we follow this thread into the longer night. As the dense smoke and dust gradually thin, another, more persistent veil remains. Sulfate aerosols high in the atmosphere. These particles will keep Earth cold and dim, setting the stage for a different kind of trial. When the primary threat shifts from poisoned air to hunger, freezing temperatures, and a world of scale we can barely imagine stripped suddenly of its giants. Now that the skies have dimmed and the fires are dying, a different catastrophe unfolds where we cannot easily see it. Beneath the darkened waves, the oceans themselves begin to fail, not with explosions or tsunamis, but with silence, as the engine that once powered nearly all marine life grinds to a halt. In the ancient seas of the late Cretaceous, the true giants of productivity were not the biggest creatures to ever walk the earth, but microscopic drifters. Phytoplankton and photosynthetic microbes floating in the sunlit surface captured light and carbon, turning dissolved nutrients into living tissue. They set the stage for almost every ocean food chain, from grazing zooplankton to colossal marine reptiles, and they helped regulate the global carbon cycle, drawing carbon dioxide from the air and locking it into shells and sediments. Now that sunlit zone collapses. Ash, soot, and sulfate aerosols scatter and absorb what little light penetrates the impact winter sky. The upper ocean, once bright enough for photosynthesis down tens of meters, becomes a dim, blue-gray twilight. Daylight at the surface drops to a fraction of normal. A few meters down, it is almost night. Cold air above chills the water, deepening the mixed layer and further diluting what faint light remains. For organisms evolved to track the daily path of the sun, this is like living under permanent storm clouds. Climate models and ocean simulations suggest that marine photosynthesis may have fallen to just a few percent of its former strength, perhaps even less, for months to years. Imagine a global ocean where the green pulse of productivity, once rising and falling with the seasons, suddenly flatlines. Primary production does not vanish entirely, but it becomes patchy, weak, and unreliable, a flicker where there was once a steady glow. The consequences cascade quickly. Zooplankton that grazed on phytoplankton find less to eat. Their populations shrink or crash. Small fish, ammonites, and filter feeders that depended on a constant drizzle of organic particles from above begin to starve. Shell beds that once sifted rich plankton blooms endure long intervals of scarcity. In the open ocean, far from coasts and rivers, this famine is most severe because almost everything there ultimately depends on that surface photosynthetic layer. Yet not every marine habitat is equally exposed. Coastal waters fed by runoff and stirred by tides may retain brief local blooms when dust thins or currents shift. In the deep sea, some communities are remarkably insulated. Around hydrothermal vents and cold seeps, chemosynthetic microbes tap chemical energy from the planet's interior, not from the sun, supporting dense assemblages of clams, tube worms, and crustaceans, even as surface waters fade. We can see this biological whiplash recorded in microfossils. Right at the thin clay line that marks the impact, many species of calcareous nanoplankton vanish. Foraminifera, the tiny shelled protists that once thrived in warm surface waters, suffer abrupt extinctions and are replaced by smaller, hardier forms better suited to low productivity conditions. The fossil record confirms what the models predict. The ocean's sun-driven engine stalled almost overnight. So in a world where light is scarce and food falls thinly through the water column, who endures? Which marine survivors can draw on alternative energy sources, slow their metabolisms, or simply outlast a famine that may span generations? Join us as we follow life into this prolonged darkness, where the next chapter of evolution begins with hunger. On land, the darkness was just as deadly. When the sky closed and the stars vanished behind a shroud of dust and soot, the oceans were not the only realms where life faced a sudden famine. The great Cretaceous forests, which had fed the biggest creatures to ever walk the earth, were about to fall silent. Before the impact, these forests were vibrant, structured worlds. Towering conifers formed high canopies, their trunks as thick as columns in a cathedral. Broad-leaved flowering trees, the angiosperms, filled the middle layers with dense foliage and seasonal bursts of color. Beneath them, carpets of ferns, low cycads, and shrubby undergrowth created a living maze. The air buzzed with beetles, wasps, and dragonflies, while caterpillars chewed through leaves and resin-rich branches snapped under the weight of browsing giants. This was not just scenery. It was the green engine of the late Cretaceous era. Then the firestorms arrived. Ejecta re-entering the atmosphere heated the air until vast regions of forest simply ignited. Not just small brush fires, but continent-spanning infernos. Whole slopes of conifers went up like torches, resin boiling and exploding, crowns joining into rolling walls of flame. In a matter of hours, lush valleys were reduced to charcoal and ash, leaving skeletal trunks, toppled logs, and open blackened ground where shade and shelter had existed for millions of years. Yet for the plants that somehow escaped the flames, the worst was still to come. With sunlight blocked, photosynthesis stalled almost everywhere. Leaves that had once turned light into sugar became liabilities, draining stored energy with no new supply. Temperatures plunged, and tissues adapted to warm, humid conditions suffered cold damage and frost kill. Then acid rain fell from skies loaded with sulfur and nitrogen compounds, leaching vital nutrients from the soil and burning delicate leaf surfaces. It was a triple blow: darkness, cold, and chemical assault striking in the same brief geological moment. Large, slow-growing trees were especially vulnerable. They had massive crowns to maintain, high energy demands, and reproductive cycles that stretched across decades. In a prolonged impact winter, there was no time for such strategies. In contrast, hardy pioneer plants with small bodies and fast life cycles had an advantage. Species that could sprout quickly, tolerate poor soils, or wait out bad years in protected stages were poised to inherit the empty ground once the skies began to clear. Among the most resilient were ferns and certain seed plants. Many ferns spread by spores and regrow from underground rhizomes insulated from heat and cold. Some seed plants carry tough, dormant seeds, able to sit in the soil until light and moisture return. Fossil pollen and spore records show a striking fern spike just above the impact boundary layer in many parts of the world, a sudden surge in fern abundance that marks the earliest phase of terrestrial recovery. This fern-dominated interval did more than repaint the hillsides. When forests collapsed, habitats vanished. Dinosaurs that browsed on high foliage lost their food and shade. Insects tied to particular trees lost their nurseries. Small vertebrates that depended on forest litter and stable, humid microclimates were exposed on a raw, open landscape. As we step back hundreds of millions of years in our minds, we can see how the death of the Cretaceous plant kingdoms set the stage for a very different Earth. If the green architecture of the Old World was stripped away in a geological instant, what kinds of communities would rise to replace it? Join us as we follow the survivors into this new, unstable chapter, where evolution works with a simpler toolkit, and every patch of sunlight becomes a battleground. With the green scaffolding of the Cretaceous stripped away, the giants that once ruled it step into a kind of slow-motion disaster. For the biggest creatures to ever walk the Earth, the impact winter does not kill in a single night. It empties their world, then lets hunger finish the work. Before the asteroid, a mature sauropod or hadrosaur was a living furnace. Not just big animals, but true titans. Their massive bodies demanded staggering amounts of fuel. A single large sauropod may have needed hundreds of kilograms of leaves and conifer needles each day, its long neck sweeping through trees the way a combine harvester moves through a field. Herds of hadrosaurs, with battery-like jaws grinding tough vegetation, could strip a floodplain in short order and then simply move on to the next. That strategy collapses the moment photosynthesis falters. When the sky fills with dust, soot, and sulfur, sunlight drops to a dull twilight. Within days to weeks, leaves wither, flowers and grasses die back, and the already burned forests no longer resprout. The plant productivity that once set the stage for a world of scale we can barely imagine falls toward zero. There is no new growth to replace what the giants tear down. Every mouthful becomes an irreplaceable withdrawal from a shrinking bank. Large dinosaurs are built to roam, but not to outrun a global famine. Their pillar-like limbs can carry them across river systems or coastal plains, yet their sheer bulk limits speed and range. A starving sauropod cannot simply march hundreds of kilometers in search of a surviving pocket of greenery before its reserves run out. Slow reproductive rates add another trap. Even if a few adults stagger into a refuge, they cannot quickly replace losses or evolve new diets in a few short generations. Their entire life history assumes a stable, productive era, not a world that has gone dark. Cold makes the vice tighter. Many paleontologists suspect that at least some large dinosaurs had elevated metabolisms, closer to birds than to modern reptiles. In a rapidly cooling climate, with ash-dimmed days and freezing nights, keeping a colossal body warm demands even more calories. Yet every extra unit of heat requires food that no longer exists. The very physiology that once allowed them to grow fast and stay active now accelerates their starvation. For the great predators, the trap is even more immediate. Tyrannosaurs and other giant theropods sit at the top of intricate food webs. When herds of hadrosaurs and ceratopsians begin to vanish, the hunters lose their primary prey almost overnight in ecological terms. They turn to scavenging, following the smell of carcasses along rivers and coasts. But each rotting body draws in multiple desperate carnivores. Competition intensifies, injuries mount, and the pool of dead giants is finite. What happens when even the corpses are gone? Could any dinosaur enclaves have persisted in sheltered valleys, coastal wetlands, or unburned forest patches? Perhaps, for a time, some river corridors still carried enough algae, ferns, and scrub to support a remnant population. Yet these oases are embedded in a global system that is failing. Ash-laden floods, acid rain, and continuing cold eventually reach them too, cut off, genetically bottlenecked, and still burdened by large size and slow breeding. Such holdouts would be measured in years at best, not millennia. In the end, the traits that had made dinosaurs supreme in the warm, lush Cretaceous, enormous bodies, specialized feeding strategies, and complex towering food webs, become fatal liabilities in the impact winter. The age of visible giants closes, even as smaller, more flexible survivors wait in the shadows. But what exactly allowed some modest feathered descendants of these titans to slip through the same catastrophe that erased their colossal kin? The answer begins in the places we almost never see. Not in the canopies where the biggest creatures to ever walk the earth once fed, but in the soil, in the roots, in the cracks between stones where the light barely reached. By the final minutes of the Cretaceous period, typical mammals were already specialists in obscurity. They were small, often no larger than a modern rat or shrew. They were nocturnal or crepuscular, active in the dim margins of day when dinosaur hunters were less alert. Many were insectivores or omnivores, darting through leaf litter, sniffing out beetles, grubs, seeds, and fallen scraps. Living in the shadows of giants had trained them for a world where staying unseen was the safest strategy. When the asteroid struck and the surface of Earth briefly became an inferno, that hidden lifestyle suddenly offered a massive advantage. Many mammals spent the day in burrows, nests, and narrow crevices. These were not just dens, they were accidental bunkers. A few meters of soil could blunt the shock of the blast wave, mute the roar of global earthquakes, and insulate against the radiant heat that ignited forests. As molten glass rained from the sky and soot thickened the air, a curled body in a tunnel of roots might feel only a distant, muffled catastrophe. In the long, toxic night that followed, those same shelters became lifeboats. Underground, temperatures fell more slowly. Airborne dust and ash were filtered by layers of sediment and rock. Even when acid rain scoured the surface, the moist walls of a burrow remained comparatively stable. A large dinosaur could not retreat into a crack in the ground, but a palm-sized mammal could vanish almost completely. Small size meant lower absolute food needs, shorter distances between safe refuges, and the ability to squeeze into spaces that fire and predators could not easily penetrate. Dietary flexibility finished what shelter and size had begun. Many early mammals were not tied to fresh green leaves or high canopies. They could feed on insects that survived in rotting wood, on seeds buried in soil, on carrion left by the collapse of entire ecosystems, and on underground storage organs, roots, tubers, and rhizomes that retained energy even as photosynthesis faltered. In a world where the impact winter choked off sunlight, these less visible food webs persisted just enough. Could anything be more valuable in an extinction than the ability to eat almost whatever you can find? The fossil record in the Paleocene period, the first chapter after the impact, confirms that this strategy worked. Many mammal lineages that crept through the late Cretaceous not only survived the bottleneck, they diversified explosively. Jaw fragments, teeth, and partial skeletons show an expansion in sizes and shapes, from tiny insect hunters to early herbivores and predators, beginning to test the vacant roles once monopolized by dinosaurs. Yet survival was never guaranteed. Some specialized groups, adapted to narrow diets or habitats, disappear from the record entirely. Their loss underlines a stark lesson. In times of sudden, global change, generalist, adaptable traits are the closest thing to insurance life can offer. Join us as we follow these survivors forward. In the dark, in the cold, packed into burrows and hollow logs, they are unremarkable to our eyes, but they set the stage for a world of scale we can barely imagine. A future in which their descendants will rise to claim open forests, sweeping plains, and eventually, the very landscapes where dinosaurs once reigned. What did that new mammal-dominated Earth look like when the darkness finally began to lift? When the darkness finally begins to lift, not every dinosaur is gone. One entire branch is still with us. We call them birds. Biologically, they are surviving dinosaurs, the last living thread of a colossal family tree severed by the impact. Before humans, before cities, before history itself, feathered theropods had already taken to the air. By the final minutes of the Cretaceous period, the sky held a variety of avian dinosaurs, some small and ground-hugging, others perched high in forest canopies, still others skimming shorelines like modern plovers and sandpipers. The extinction did not erase them all. Instead, it split their lineage from every other non-avian dinosaur group, drawing a hard line between what would endure and what would vanish forever. Fossils show that many of the birds hugging the ground or patrolling beaches and river margins were compact, wary, and unspecialized. They resembled stout, shorebird-like forms more than the massive soaring giants we might imagine. In a world where trees are stripped bare, fires rage, and ash chokes the air, which lifestyle is more resilient? A small cautious forager on the ground, or a large canopy-dwelling specialist that needs stable forests and steady winds? The rock record suggests the answer. Key to their survival were beaks and guts built for hard times. Many late Cretaceous birds could crack seeds, nip tough shoots, and probe for buried invertebrates. Seeds can lie dormant in the soil, protected from fire and frost. Tough stems and rhizomes persist, even as leaves vanish. Insects and worms shelter underground. Birds that could process these durable, low-light resources had a lifeline when fresh foliage disappeared, and most herbivorous giants starved. Join us as we trace how such modest dietary flexibility became a decisive advantage. Flight itself, though hampered by ash-filled skies and a dim, cooling earth, still mattered. Wings meant mobility. Even if long-distance soaring was impossible under a shrouded sun, short, powerful flights allowed survivors to hop between scattered refuges. A half-frozen pond here, a carcass there, a patch of unburned scrub beyond the next ridge. In a fractured, hostile landscape, The ability to leave a dying patch of habitat and reach a slightly better one could mean the difference between lineage and oblivion. Reproduction added another edge. Many of these birds laid multiple eggs, nested on or near the ground, and produced young that matured rapidly. In an era of repeated shocks, cold snaps, toxic rains, failed food patches, being able to rebound quickly when conditions briefly improved allowed tiny populations to expand into newly open niches. Non-avian theropods and the large-toothed, tree-dwelling birds, closely tied to forest canopies and abundant prey, were far less forgiving of disruption. They needed stable hunting grounds, tall trees, and predictable seasons. When those collapsed, their specialized bodies and slower life cycles left them exposed. Molecular clocks and the sparse fossil record agree. Only a few hardy bird lineages slipped through that razor-thin bottleneck at the boundary, then fanned out in the Cenozoic to become songbirds, raptors, waterfowl, and the countless forms alive today. But if birds and mammals endured, what happened to the colossal reptiles that still lurked in the water, waiting in the murk as the first night after impact unfolded? As forests burned and the last colossal dinosaurs fell silent on land, another kind of reptile waited in the shadows of rivers and swamps. Not sprinting across open plains, but hovering just beneath the surface, eyes and nostrils breaking the water like tiny periscopes. While the biggest creatures to ever walk the earth vanished above, these lurkers in the murk were about to prove that survival sometimes favors patience over power. In the late Cretaceous, crocodilians and turtles were already widespread, settled into lakes, slow rivers, and coastal wetlands on nearly every continent. Before humans, before cities, before history itself, the Earth's lowlands belonged to these ambush hunters and bottom dwellers, lying in wait among reeds and tangled roots. Some crocodilians were massive, broad-snouted predators that could drag a hadrosaur under in a single explosive lunge, while turtles ranged from small mud-colored pond dwellers to heavier river forms with thick shells like living shields. Together they inhabited a world of scale we can barely imagine, yet they kept close to the water's edge. When the asteroid struck and the first night began, that water became more than habitat. It became armor. As superheated ejecta turned skies into a broiler and wildfires swept across continents, ponds and rivers acted as thermal buffers, absorbing heat and moderating the violent temperature swings that scoured the land. A crocodile pressed against the muddy bottom, or a turtle tucked beneath a ledge, would feel the shock waves and see the dimming light, but the water above them blunted the worst of the blast, the flying debris, and the searing winds. Even as acid rain began to fall, dilution in larger water bodies softened its sting. Yet it was not shelter alone that saved them. Crocodiles and many turtles possess a remarkable ability to slow their metabolism, slipping into torpor when conditions turn harsh. They can hold their breath for long stretches, lower their heart rate, and survive on minimal oxygen and food. In a world where plants withered and prey animals died in droves, that low-energy strategy was priceless. A crocodile could endure weeks or months between proper meals, scavenging whatever carrion washed into its pool. A turtle could sit half-buried in sediment, waiting for the chaos above to ease. How many other reptiles could afford to be so patient? Their diets helped as well. These were not picky specialists, balanced on a single food source. They were generalists. Fish, invertebrates, amphibians, small vertebrates, decaying carcasses torn from upstream kill zones. Almost anything that drifted or swam by could be turned into calories. Even as primary productivity crashed on land, nutrient-rich, sheltered waterways still received pulses of organic matter from dying forests and floodplains. Join us as we imagine those dark channels where life continued in slow motion while the surface world burned and froze. Even their eggs and young found refuge. Many crocodilians and turtles buried their clutches in sandbars, riverbanks, or mounds of vegetation, insulating them from sudden temperature spikes and shielding them from direct contact with acidic rainfall. Hatchlings could hide in submerged roots or dense aquatic plants, protected from falling ash and the worst atmospheric toxins. In this shattered era, every extra layer of mud, sand, or water between a fragile body and the open air increased the odds of making it to the next day. Still, not all aquatic life survived this extinction. Specialized marine reptiles that roamed the open oceans and the coiled ammonites that had thrived for hundreds of millions of years disappeared entirely. Their high energy demands and narrow ecological niches left them exposed when food webs collapsed. Flexibility, low metabolic needs, and a willingness to eat almost anything proved far more valuable than speed or size. The persistence of crocodilians and turtles through that first night set the stage for their continued presence today. When you watch a crocodile glide through a murky river, or see a turtle resting motionless on a pond bottom, you're looking at lineages that endured one of Earth's darkest nights and stepped into the new Cenozoic world. What other survivors, hidden in burrows or clinging to charred trees, were preparing to reshape the planet alongside them? What happens to a planet when almost everything dies at once? Not just the giants, but the forests that fed them, the plankton that colored the seas, the living green skin of Earth itself. In the choking darkness after impact, when photosynthesis faltered and primary productivity collapsed, life did not stop. It shifted. It moved into the shadows and into the soil. Before humans, before cities, before history itself, there was another kind of ecosystem waiting in the wings. Detritus-based worlds, where dead organic matter rather than living leaves powered the flow of energy. In these grim food webs, carcasses, fallen leaves, and shattered branches replaced fresh foliage and sunlit plankton as the foundation of life. The asteroids' firestorms and shockwaves suddenly supplied these systems with a massive, macabre bounty. Across the continents, dinosaur bodies lay where they fell. Forests that had shaded hadrosaurs and armored ankylosaurs were reduced to blackened trunks and heaps of dead wood. In the oceans and lakes, fish, ammonites, and planktonic communities collapsed, raining organic debris down onto the seafloor. This was an enormous pulse of detritus, a planet-wide layer of raw material ready for fungi, bacteria, and scavenging insects to exploit. In the long impact winter that followed, darkness, cooler temperatures, and nutrient-rich surfaces created ideal conditions for many decomposers. Fungi do not need sunlight. They need carbon, moisture, and time. Their thread-like hyphae spread through buried roots, carcasses, and leaf litter, secreting enzymes that broke tough tissues into simpler compounds. Microbes joined them, forming invisible films on every surface, turning muscle into slurry, bone into mineral, and locked away nutrients back into soils and sediments. Fossil cores taken across the Cretaceous-Paleogene boundary preserve a remarkable signature of this hidden boom. In some regions, layers just above the impact horizon are packed with fungal spores, a so-called fungal spike that suggests a temporary surge in decomposer activity. Insect fossils and trace marks on leaves and wood also change, hinting that many specialized plant feeders vanished, while hardy scavengers and detritivores, such as beetles and fly relatives, took their place. These insects were not only recyclers, they became food. Small mammals emerging cautiously from burrows, early birds clinging to scorched branches, and lizards hunting among the ash all found critical calories in maggots, beetle larvae, and adult scavengers clustering on carcasses. When green plants were scarce or absent for weeks, months, even years in some regions, this detritus-based chain kept energy moving through ecosystems. In a world of scale we can barely imagine, where the biggest creatures to ever walk the earth had just vanished, it was the tiny decomposers that quietly set the stage for recovery. By the time light slowly filtered back and surviving plants began to sprout in sheltered pockets, the soils beneath them were enriched, microbially active, and primed for growth. As we follow the story forward, how would these dark, fungal years shape the speed and pattern of Earth's return to green? But enriched soil alone could not protect a wounded planet. As the ash-thick skies slowly thinned and pale light returned, the first shoots of green emerged into a world stripped of its armor. Before the impact, roots laced through ancient floodplains and forested hillsides, binding grains of sand and clay together. After the impact, those roots were gone. Whole slopes that had held firm for millions of years were suddenly loose, unstable skin on the face of the earth. Without plant cover, every raindrop became a hammer. And the rains were not gentle. In the first years after the impact, the atmosphere was loaded with sulfur and dust, turning water vapor into acid-laden storms that lashed the continents. Imagine hillsides where titanosaurs once walked, now liquefying into rivers of mud, sliding downslope as landslides and debris flows that could bury valleys in a single night. Where snow and ice formed during sudden cold snaps, brief thaws unleashed pulses of meltwater that surged through canyons, carving them deeper in decades than normal climates might in thousands of years. Rivers responded like overloaded conveyor belts. They swelled with churning, opaque water, so thick with sediment that the channels themselves began to wander and split. Join us as we follow those currents, carrying colossal volumes of mud, sand, charcoal, and shattered wood from the barren uplands into lowlands, lakes, and shallow seas. In some places, former clear water streams became braided torrents tens of kilometers wide, their shifting bars burying carcasses of dinosaurs, crocodiles, and fish beneath fresh layers of silt before scavengers could reach them. These were not neat, orderly deposits. They were chaotic, jumbled records of catastrophe. As flood after flood swept across the landscape, they laid down thick packages of sediment studded with shocked minerals from the impact. Glassy spherules of condensed rock, fragments of burned forests, and broken bones from multiple habitats mixed together. Today, when geologists trace the boundary between the age of dinosaurs and the age that followed, they often find exactly this kind of layer, a smeared, tangled snapshot of a world in violent transition. In that chaos, preservation and removal went hand in hand. Many carcasses and fallen trees were rapidly entombed, sealed away from decay and locked into the fossil record. Others were ground apart or swept out to sea, stripped from surface ecosystems that desperately needed every remaining scrap of organic matter. What new landscapes emerged from this reshaping? As channels shifted and basins filled, fresh lakes, wetlands, and river plains appeared where none had existed. Quiet backwaters amid the turmoil, waiting to be colonized by the survivors of the extinction. In a single geological heartbeat, erosion, floods, and sedimentation did more than scar the surface. They rewrote it. The impact did not simply remove the biggest creatures to ever walk the earth. It set the stage for a new map of environments, a rearranged canvas on which evolution would paint the next chapter of life's story. So how did the first pioneers move into these raw, unstable habitats? And what did recovery look like on this freshly sculpted world of scale we can barely imagine? To trace that recovery, we do not just imagine the first night after impact. We read it, layer by layer, grain by grain. The story of catastrophe and survival is written into the rocks beneath our feet, across the planet, from Italy to New Zealand, from North America to India. We find the same thin, often centimeter-scale band of clay and mixed sediments. This is the KPG boundary layer, the razor-thin line between two worlds. Below it, the last days of the dinosaurs. Above it, an Earth remade by extinction. That narrow strip of rock marks the moment the impact's shockwave raced around the globe and the age of giants ended. Inside that boundary, the signals of violence are unmistakable. We see an enrichment of iridium, a rare element on Earth, but common in asteroids, spiking to levels far above normal crustal rocks. We see grains of shocked quartz, crystals whose internal structure has been deformed by pressures like those in nuclear tests. We see microtectites and glassy spherules, tiny beads formed when molten rock was blasted into the sky, cooled as it rained back down, and settled through the darkened seas. Together, they are physical proof that an extraterrestrial body struck with colossal force. Yet the boundary is not only a record of impact, it is also a record of what burned. Mixed into that clay are layers of soot and charcoal, microscopic black fragments of forests and peatlands that caught fire on continents thousands of kilometers from Chicxulub. Certain organic molecules act as chemical fingerprints of burned plant material, revealing that vast amounts of biomass went up in flames. Can we picture whole landscapes, from conifer woods to coastal swamps, turning into a global ring of fire within hours? Just above and below that line, the fossils themselves change abruptly. In marine sediments, diverse plankton communities vanish, replaced by a few hardy species that can tolerate low light and stressed oceans. On land, pollen from flowering plants and conifers drops, while spores from ferns surge in what paleontologists call a fern spike, a botanical takeover by opportunistic survivors. Microfossils become a census of loss and renewal, showing us which branches of evolution were cut short and which clung on. The chemistry of these layers adds another dimension. Ratios of carbon, oxygen, and sulfur isotopes shift suddenly, recording a rapid cooling of surface waters, disruptions to ocean circulation, acidified rain, and a global carbon cycle thrown out of balance. These subtle variations tell us that the impact winter was not just dark, it was cold, corrosive, and prolonged. To understand timing and magnitude, we turn to models. Computer simulations of atmospheric dust, soot, and sulfur aerosols calculate how fast the skies would have dimmed, how deeply the oceans would have chilled, how long photosynthesis would have stalled. Then we test those virtual worlds against the rock record. Do the isotopes, the fossils, and the boundary clay agree? When they do, we gain confidence in the sequence of nights, seasons, and years that followed. Every grain of that boundary clay is a time capsule, preserving echoes of the firestorm dusk, the first sunless midnight, and the grueling years of recovery. Join us as we follow those echoes forward, from chemical chaos to the first resilient ecosystems that would set the stage for a new cast of dominant life. Which survivors would rise to shape the next era on this wounded Earth? Those echoes carry us into the slow turning of the sky, from endless night and toward a hesitant dawn. The catastrophe did not simply stop. It faded, grain by grain, droplet by droplet, as Earth tried to clear its own wounded air. In the first months after impact, the atmosphere was choked with a complex mix of debris. Heavier ash and soot, blasted from burning forests and pulverized rock, began to fall out first. Each flake of black carbon, each shard of dust, surrendered to gravity and drifted back to the shattered ground, forming thick, dark layers over land and sea. Above them, far finer sulfate aerosols, born from vaporized sulfur-rich rocks at Chicxulub, lingered much longer, scattering sunlight and keeping the planet in a prolonged artificial twilight. Rain became one of the main sculptors of this new sky. As storm after storm swept the globe, water droplets captured sulfate particles and washed them downward, sometimes as acid rain, sometimes as more neutral showers once the worst chemistry had passed. Over months, then years, this relentless cleansing allowed the densest veil to thin. The change was not dramatic from one day to the next, but over seasons, the difference was unmistakable. At first, the darkness was nearly absolute. Noon felt like a moonless midnight. Then, slowly, the sky shifted to a dull, oppressive gloom, where you might barely make out the outline of a broken tree or a jagged hillside. As more particles settled and more aerosols decayed, that gloom brightened into a murky grayish glow. Eventually, pale filtered sunlight began to pierce the haze, like a weak lamp behind frosted glass. Can you imagine the first day when shadows, however faint, returned to the ground? With every additional ray of light, more solar energy reached the surface. Global temperatures, which had plunged in the immediate impact winter, began to rebound. The climate remained cooler than the lush, late Cretaceous and wildly unstable, with sharp swings between seasons and regions. But the most lethal cold eased. This fragile warming set the stage for the first visible signs of ecological recovery. On land, the pioneers were not towering conifers or flowering trees, but low, resilient plants. Ferns, which thrive in disturbed, nutrient-rich soils, spread in vast carpets over burned hillsides and ash-covered plains. In some fossil layers, we see literal fern spikes, where fern spores suddenly dominate the record, marking this botanical comeback. Hardy shrubs and small, fast-growing angiosperms followed, their roots prying into cracked sediments, their leaves capturing every scrap of returning light. In the oceans, the story unfolded in parallel. Surface waters, once starved of light, slowly brightened as the atmospheric shroud thinned. Certain phytoplankton groups, especially small opportunistic species, were among the first to rebound, re-establishing the base of marine food chains. Tiny crustaceans and filter feeders followed, then small fish, rebuilding communities that had nearly collapsed when photosynthesis stalled. Yet this was not a simple restoration of the old Cretaceous world. Many lineages were gone forever. The biggest creatures to ever walk the earth, the colossal non-avian dinosaurs, never returned. In their absence, survivors stepped into newly opened roles. Small mammals, once overshadowed, began to diversify. Bird lineages that had made it through the darkness took to the air above altered forests. Crocodilians, turtles, and extraordinarily resilient plants and microbes persisted along rivers, lakes, and coastlines, anchoring food webs in this transformed era. We step back hundreds of millions of years in our imagination, yet this moment feels strangely close, because from this dim, fragile dawn after the dinosaurs last night, a new world would rise. How did these survivors, shaped by disaster, launch the age of mammals and, eventually, the path that leads to us? Join us as we follow them into that unfolding story, where each adaptation becomes a stepping stone toward a world of scale we can barely imagine. From that fragile dawn, we pull the camera back and look at the whole planet. The asteroid did not just erase the biggest creatures to ever walk the Earth. It rewrote the surface of the world itself. Not slowly, over millions of years, but in a geological instant. Impact Winter was the architect. With soot-darkened skies circling the globe, sunlight collapsed to a dim twilight. Temperatures plunged. Photosynthesis stalled on land and in the sea. When plants stop capturing energy, landscapes stop behaving the way we know them. Soils that were once held in place by roots and tangled undergrowth suddenly loosened, ready to move with every storm and flood. Have we ever seen an entire biosphere lose its grip on the ground so quickly? Around the coasts, the violence was even more direct. The Chicxulub impact hurled walls of water outward, mega tsunamis that rose hundreds of meters near the crater and still towered as they raced across ancient seaways. They surged far inland, scouring shorelines, ripping up forests, and dumping chaotic mixtures of sand, boulders, and shattered shells into low-lying basins. Seismic shockwaves rattled continental margins, triggering underwater landslides that sent dense slurries of mud and debris hurtling into the depths. These sudden pulses left one of the sharpest bookmarks in Earth's history: the KPG boundary, a thin, distinctive layer that we can trace in rocks on every continent. On land, the collapse of forests completed the transformation. First came the firestorms, ignited as superheated ejecta fell back through the atmosphere. Then came frost, as the soot-shrouded planet cooled, and acid rain as vaporized rock and sulfur mixed with the clouds. Trunks toppled, canopies opened. Hillsides that had been anchored by roots for tens of millions of years were stripped almost bare. With every downpour, massive erosion pulses began, sending torrents of mud, ash, and charcoal into rivers. Those rivers swelled and darkened, choked with the remains of a lost era. They carried nutrients, soot, and the carbonized ghosts of forests into deltas and shallow seas. Join us as we imagine those coastlines, estuaries turning to liquid soil, bays infilled almost overnight, new wetlands forming where clear water had once lapped at sandy beaches. This was not just destruction. It was the rapid remodeling of entire drainage networks, the carving of new channels that would set the stage for future ecosystems. The oceans themselves shuddered under the shock. Surface waters cooled abruptly under the darkened sky, while deeper layers lagged behind, disrupting circulation patterns that had persisted for ages. Plankton, starved of light, died in vast numbers and drifted downward with the constant rain of ash and microscopic glass. On the seafloor, this global fallout settled into a thin, clay-rich band laced with iridium from the asteroid and specks of soot from burned continents. That quiet, deadly rain recorded the moment of extinction in a line no thicker than a finger. When the skies finally began to clear, Earth's landscapes and seascapes were already remade. Coastlines had shifted, rivers had redrawn the maps, and the oceans wore a new chemical and sedimentary signature. In this scarred terrain, with the old order buried beneath a single boundary layer, the long ecological reset could finally begin. What kinds of communities would rise from these altered plains and seas, and how would they build the foundation for our own mammal-dominated world? To answer that, we have to follow life into the first recovering forests and the dark, uneasy oceans that came next. To understand the new communities rising in those uneasy oceans and shattered forests, we have to face the brutal arithmetic of who lived and who died. Not just a story of bad luck, but of bodies, habits, and habitats meeting forces far beyond their design. The impact unleashed a chain of kill mechanisms that swept across the ancient world. First came the thermal pulse. Ejecta falling back through the atmosphere heated the sky, turning it into a broiler that likely ignited global wildfires. For animals exposed on the surface, especially large dinosaurs and other colossal reptiles, there was nowhere to hide from a curtain of radiant heat. Then came the smoke and dust, plunging Earth into an impact winter, months of darkness, freezing temperatures, and toxic atmospheric chemistry, including acid rain, stripped leaves from branches, poisoned waters, and shut down photosynthesis on land and in the upper ocean. For the giants that had ruled the late Cretaceous, each step in this cascade was a trap. Large herbivorous dinosaurs needed massive quantities of fresh vegetation every day. When forests burned and grasslands withered, their sheer bulk became a liability. Apex theropods perched at the top of the food web starved next, dependent on prey that was already disappearing. Reptiles tied to sun-warmed bodies in open air, flying pterosaurs, many large marine reptiles near the surface, armored dinosaurs on floodplains, were exposed to heat, smoke, and then bitter cold in rapid succession. By contrast, being small, generalist, and low on the food chain suddenly became a powerful survival strategy. Small bodies meant lower energy needs. A shrew-sized mammal or sparrow-sized bird could survive on scraps that would not sustain even a juvenile dinosaur. Generalist diets, seeds, roots, carrion, insects, offered flexibility when green plants vanished. And crucially, many of these creatures could hide. Burrows, crevices, deep leaf litter, and water acted as shields against the thermal pulse and wildfires. In the worst hours, safety was measured in centimeters of soil or meters of water. Join us as we look at the key survivor groups that slipped through this evolutionary bottleneck. Small mammals, already nocturnal and often burrowing, endured the darkness with efficient, warm-blooded physiology and flexible appetites. Birds, the only dinosaurs to survive, combined high metabolic rates with the ability to eat seeds and invertebrates, and some could shelter in dense vegetation or rock cracks. Crocodilians rode out the catastrophe in rivers and lakes, able to slow their metabolism and weight, submerged and patient. Turtles, some amphibians, and many fish and invertebrates persisted in aquatic refuges, buffered from the worst temperature swings and fires. In the end, the extinction funneled entire branches of evolution through a few narrow lineages. This is the essence of an evolutionary bottleneck, a colossal diversity crushed down to a handful of surviving threads, each carrying the genetic legacy of countless lost relatives. From those threads, new worlds of life would unfold. But what did these battered survivors actually do with their unexpected second chance? And how quickly could they rebuild a world of scale we can barely imagine? Those surviving threads were not all hidden in burrows or armored in bone. Some of them still wore feathers. In the darkness after impact, while the age of the colossal land giants was collapsing, a very different kind of dinosaur was quietly outlasting the catastrophe above the ash-covered Earth. Birds are not just relatives of dinosaurs, they are dinosaurs. Avian theropods, descended from the same predatory lineage that produced Velociraptor and Tyrannosaurus, passed through the extinction filter when their larger cousins did not. When we say the dinosaurs went extinct, we are really saying that almost every branch of their family tree was sheared away, leaving a single adaptable twig that would eventually seed the skies of the modern world. The birds most likely to survive that first night were not the spectacular toothed flyers of the late Cretaceous forests, not the specialized tree-perching forms whose lives depended on dense canopies that were now charred and falling. Instead, the survivors were probably small, ground-dwelling or semi-aquatic species, hugging river margins, lake shores, and coastal wetlands, where water and mud could buffer fire and shock. Many of them would have had sturdy beaks rather than toothy jaws, mouths shaped to crack seeds, sift detritus, or pick at almost anything edible they could find. This difference in diet mattered. In a world where flowers withered, fruits vanished, and insect populations crashed, seeds and buried plant material became lifeboats of energy. Seeds can lie dormant through fire and frost. They can ride out impact winter in the soil. A bird that could scratch through ash, probe mud, and swallow hard, dry kernels had a crucial advantage over a delicate nectar specialist or a forest insect hunter suddenly deprived of both trees and prey. Other traits stacked the odds in their favor. Birds reproduce quickly, laying multiple eggs in a single clutch. Even if many nests failed, a few surviving broods could rebuild numbers in just a few breeding seasons. Their lightweight, air-filled bones and powerful muscles allowed them to move, to flee local devastation, to track shrinking patches of habitat across a fractured landscape. Mobility meant choice. In an era of global crisis, being able to leave was life itself. Just as important was flexibility. Many early surviving lineages appear to have been ecological generalists, able to switch between seeds, carrion, invertebrates, and shoreline scraps. In an environment where almost every familiar food web had snapped, this capacity to improvise set the stage for long-term success. We can ask, which animals thrive when everything changes overnight? Again and again, the answer is those that can eat almost anything, breed fast, and move far. From these quiet, ash-dusted survivors, the astonishing diversity of modern birds unfolded. Join us as we step back hundreds of millions of years in our minds and then race forward, watching these modest Cretaceous holdouts radiate into songbirds that fill forests with sound, raptors that rule the air like miniature theropods, and waterfowl that reclaim the lakes and seas. The biggest creatures to ever walk the earth were gone, but their feathered descendants would claim the skies. How then did the other survivors, mammals, crocodiles, and more, reshape the ruined continents alongside them? In that first unnatural night, as forests smoldered and ash drifted down like black snow, another kind of survivor waited in the dark. Not the towering reptiles that had ruled the continents, but the small, the quiet, the hidden. For more than 100 million years of the Mesozoic era, mammals had already shared this ancient world with the dinosaurs. Yet they lived almost entirely in the ecological shadows. Before humans, before cities, before history itself, the Earth belonged to giants, not just big animals, but true titans. While the biggest creatures to ever walk the Earth thundered overhead, most mammals were mouse to badger-sized, nocturnal, insectivorous, or omnivorous, slipping through leaf litter and under roots. They hunted beetles instead of hadrosaurs, nibbled seeds instead of cycads, and emerged mostly under cover of night to avoid the claws and teeth of their colossal neighbors. Those very habits now became a lifeline when the thermal pulse raced around the globe and wildfires leapt from continent to continent. Many mammals were not out in the open plains, they were underground. Burrowing species had excavated nests in soil and sand, tunnels that buffered them from searing heat, choking smoke, and the deadly hail of ejecta. Even species that did not dig deeply often sheltered in crevices, hollow logs, or dense undergrowth, places that blunted the worst of the blast furnace above. Their eyes and brains were already tuned to darkness. Being nocturnal meant that navigating by smell, touch, and sound was normal, not an emergency adaptation. As the skies dimmed and impact winter began to grip the planet, these animals continued to forage under starlight and ash clouds, following familiar scent trails where diurnal creatures were suddenly blind. Diet was another quiet advantage. Many early mammals were flexible omnivores. They could crack tough seeds that survived the fires, pick insects from rotting wood, scavenge carrion from dinosaur carcasses, and even sift through detritus along riverbanks. In a world where lush vegetation had collapsed, this ability to eat almost anything edible set the stage for their persistence when specialists starved. Size, which once seemed a disadvantage next to sauropods and tyrannosaurs, now became a demographic strength. Small bodies require less food, lose heat quickly, and can hide in tiny refuges. Short lifespans and rapid reproduction meant that, once even minimal food webs reassembled, mammal populations could rebound in years rather than centuries. While the age of reptilian dominance ended in a geological instant, mammalian evolution accelerated into the empty niches left behind. Join us as we step back hundreds of millions of years in our minds and look forward at the same time. From these unremarkable shrew-like survivors will eventually emerge bats that own the night sky, whales that rival ancient marine reptiles in size, and primates that will one day ask how any of this was possible. How did a handful of furtive creatures, huddled in burrows on that first night after extinction, ultimately give rise to us? And what other survivors were quietly preparing their own rise in the shadows? But those mammals in their burrows were not alone in finding shelter on that first catastrophic night. While the land burned and the air itself became a weapon, another refuge waited in plain sight, spread across the ancient world in rivers, lakes, wetlands, and coastal lagoons. Water, which had cradled life since its beginnings, now became a shield. Before humans, before cities, before history itself, the Earth belonged to giants that strode across floodplains and forests. Yet in the hours after impact, it was not size that mattered most, but insulation. A layer of water only a few meters deep could blunt the worst of the thermal pulse, absorb flying debris, and soften the shock of pressure waves racing through the atmosphere. While forests flashed into flame and surface temperatures spiked, just below the surface, the water remained comparatively stable, a dim green twilight instead of a furnace, Join us as we follow one of the most unlikely groups of survivors, the crocodilians. These semi-aquatic reptiles had already endured tens of millions of years of climatic swings by the end of the Cretaceous period. On that night, their very design set the stage for survival. With slow metabolisms, they could go weeks or even months with little food. They could slide into deep pools, hug the bottom, and wait while superheated winds and burning embers scoured the banks above. Some would have used burrows or mud hollows at the edges of rivers and swamps, sealed off from the worst of the heat and ash. A crocodilian can lower its heart rate, close nostrils and eyes, and ride out long intervals of low oxygen. In a world where many animals died in minutes from searing temperatures and choking smoke, the ability to simply shut down and wait was a colossal advantage. Turtles and many amphibians found similar havens. Freshwater turtles could bury themselves in the soft, cooling mud at the bottom of ponds, slipping into a hibernation-like state that they already used to survive droughts and winter freezes. Some amphibians were expert burrowers, retreating deep into moist soil or flooded burrows where the temperature spike was muted and the rain of molten glass could not reach. Others escaped into deeper water where darkness fell quickly, but lethally high temperatures did not. Their low energy needs and flexible diets turned out to be critical. When the impact winter began, when sunlight faded behind a veil of dust and soot and plant life collapsed, these animals did not require constant, rich food supplies. Many could subsist on decaying matter, carrion washed into lakes, or the last struggling invertebrates in the mud. In a world of scale we can barely imagine, where the biggest creatures to ever walk the earth lay dead on the shores, these modest survivors endured. Yet survival did not mean comfort or safety. Many crocodilian, turtle, and amphibian lineages still vanished in the long shadow of extinction that followed. But the ones that made it through show us how life clings to refugees, how evolution favors any strategy that can exploit a pocket of stability in chaos. As the surface cooled and the long night deepened, other, more unexpected refugees were also sheltering life for the world to come. Those refugees were the seeds of a very different future. When we step back from the terror of that first night and look ahead, we see something just as dramatic as the impact itself. A planet stripped down to the basics, then slowly, patiently, rebuilding the web of life. Before the impact, the Earth belonged to giants, not only the biggest creatures to ever walk the Earth, but entire forests, reefs, and river systems shaped around them. In the aftermath, that complexity collapsed. With the great herbivorous dinosaurs gone, vast landscapes lost their main plant eaters and the colossal predators that hunted them. Charred, deforested hillsides stretched for hundreds of kilometers. Food webs that had once linked towering trees, herds of hadrosaurs, and stalking tyrannosaurs shrank into simple chains dominated by detritus, fungi, hardy ferns, and a few scrappy flowering plants clinging to ash-choked soils. In this simplified, shattered world, recovery began from the bottom up. First came the decomposers, the bacteria and fungi that fed on a planet-wide layer of dead wood, dead animals, and dead plankton. Their work released nutrients back into the soil and sea, setting the stage for the first green return. Pioneer plants, especially ferns and fast-growing weeds, spread across floodplains and along river margins, forming low carpets where once there had been forests tens of meters high. Have you ever seen a burned hillside flush green within a year? Multiply that by continents, and you glimpse the early steps of this ancient reset. As plants reclaimed patches of ground, insects and other invertebrates followed. Beetles, flies, and ants exploited rotting material and new shoots, while small scavenging vertebrates, surviving lizards, mammals, and birds, picked through carcasses and detritus. Over tens of thousands of years, scattered plant communities linked up, shade returned, and with it came more structured habitats. Only then could more complex food webs reappear. Pollinators and seed eaters, small predators, And eventually, in some regions, new large herbivores and carnivores descended from lineages that had once been minor players. With the non-avian dinosaurs gone, evolution found empty ecological stages everywhere. Mammals, once mostly small and nocturnal, began to radiate. Some remained tiny insectivores, but others pushed into roles once held by mid-sized dinosaurs, growing into dog-sized omnivores, then over millions of years, into the massive herbivores and formidable predators of later epochs. Birds, the surviving branch of theropod dinosaurs, diversified into ground runners, climbers, swimmers, and soaring fish hunters, exploring a world of scale we can barely imagine without their ancient cousins overshadowing them. Plants, especially flowering plants, experimented with new forms, thicker woods, different leaf shapes, novel fruits and seeds, shaping and responding to these new animal partners. This rebuilding was not quick. It took hundreds of thousands of years just to restore basic forests in many regions, and millions of years before, ecosystems rivaled the complexity of the late Cretaceous. The first night after the dinosaurs went extinct was only the opening chapter of a long planetary reset. What new stories did that reset allow? Stories that would eventually lead to us and to the next era of giants. Join us as we follow that trail into the Cenozoic, where the age after dinosaurs truly begins. To follow that trail into the Cenozoic, we first have to read the ashes left behind. Before mammals rise and new giants claim the Earth, we return to a single haunting line in the rocks: the global KEPG boundary. Around the world, from Italy to New Zealand, from North America to the deep Atlantic, there is a razor-thin band of clay that marks the night the dinosaurs fell. Not a thick lava flow, not a massive sandstone cliff. A layer sometimes no wider than your fingernail, yet packed with clues. In it, we find iridium, a metal rare in Earth's crust, but common in asteroids, spiking to levels far above normal background. We find shocked quartz, crystals whose internal structure has been shattered by pressures seen only in colossal impacts and nuclear tests. We find glassy microtectites and spherules, tiny frozen droplets of once molten rock that rained from a sky on fire. We even find soot, a global dusting of burned forests, and in coastal regions, chaotic tsunami deposits where ocean and land briefly traded places. How do we turn that thin line into a minute-by-minute story of the first night? Join us as we follow several independent lines of evidence that, together, set the stage for a world of scale we can barely imagine. At Chicxulub itself, buried under younger sediments on the Yucatan Peninsula, the crater preserves the geometry of Violence, a multi-ring basin, uplifted central peak, and a blanket of breccia recording rock that behaved like a fluid. Drilling into this structure, scientists recover cores that show melted rock overlain by tsunami sands and then by the global clay, locking in the order of events. Far from the crater, deep-sea sediment cores act as quiet logbooks. Changes in grain size, chemistry, and fossil content reveal when the oceans went dark and how long productivity crashed. Isotope ratios in carbon and oxygen help us reconstruct temperatures and the collapse of food webs, indicating a rapid surface ocean cooling and a long, drawn-out recovery. In some places, tiny shells of plankton vanish abruptly at the boundary, replaced by a near-lifeless gap. On land, fossil assemblages shift just as suddenly, with non-avian dinosaurs disappearing between one layer and the next. Some discoveries bring us right into the first hours. In North Dakota, exquisitely preserved fish lie in a storm-tossed deposit, their gill regions packed with impact spherules that match Chicxulub ejecta. These animals seem to have suffocated as glassy droplets rained into the water. Nearby, tree trunks are entombed in charcoal and ash. Entire forests flash frozen in the aftermath of wildfires that swept continents. Elsewhere, fern spores explode in abundance just above the boundary. A fern spike, showing how hardy plants rapidly colonized a burned landscape. When we imagine the sky blazing, the sudden darkness, and the bitter cold that followed, we are not inventing a disaster movie. We are translating chemistry, shattered minerals, and silent fossils into a narrative. Each new core, each refined isotope curve, tightens the timeline. How quickly the air filled with dust, how long the nights stayed dim, how selectively the extinction cut through different groups. And this detective work is not finished. As we continue to probe the boundary, we sharpen our view of that first night and prepare to watch the age after dinosaurs unfold in even greater detail. And when we sharpen that view, something astonishing comes into focus. The story of that night is not just about loss. It is about the world we live in right now. Before humans, before cities, before history itself, the Earth belonged to giants. Not just big animals, but true titans. The biggest creatures to ever walk the Earth ruled the land, while massive marine reptiles and ammonites filled the seas. When that rock from space ended their reign, it did more than erase an era. It reset the rules of life. Without the removal of the non-avian dinosaurs, mammals might have remained in the shadows forever, small, nocturnal, and constrained by colossal neighbors. In the silence after extinction, those survivors began to expand. Lineages that had hidden in burrows and under ferns now spilled out into empty habitats. Over millions of years, they diversified into hoofed grazers, climbing primates, and eventually great apes. Our own story, the rise of primates and the appearance of humans, is inseparable from that ecological reset. If tyrannosaurs and titanosaurs had continued to dominate, would a bipedal primate with a curious brain ever have emerged? The odds would have been very different. The impact also tore apart and rebuilt ecosystems themselves. Join us as we trace how the post-impact world set the stage for modern forests, grasslands, and oceans. In the early Paleogene, forests that regrew after global wildfires were denser and darker, favoring birds and mammals that could navigate branches, glide, or climb. Later, as climates cooled and dried, grasses spread across continents, creating vast open plains. Herds of large grazing mammals evolved to exploit these new food webs, their chewing teeth and complex stomachs turning tough grass into movement, migration, and heat. In the seas, the loss of many marine reptiles and plankton groups opened space for new communities. Modern coral reefs, rich in fish diversity, and today's patterns of ocean productivity are part of a long recovery from that single catastrophic night. As plant types shifted and new forests and grasslands expanded, the global carbon cycle changed, altering atmospheric carbon dioxide and nudging climate trajectories for tens of millions of years. Many of the groups we consider iconic today are, in a sense, children of the crater. Songbirds radiated into the skies of the Paleogene, filling acoustic niches in forests that had only recently burned. Flowering plants evolved new forms and partnerships with insects, giving us fruit-bearing trees, colorful meadows, and complex pollination networks. Large grazing mammals, from antelopes to bison, are products of this post-impact experimentation, thriving in landscapes that dinosaurs never saw. So when you look at a bird in the sky, you are watching a living dinosaur, a survivor of that ancient crisis. When you see a squirrel, a whale, or your own reflection, you are seeing a lineage that only rose because others fell. We step back hundreds of millions of years to understand that our cities, our crops, even the air we breathe, are part of a story that began when night fell on the age of dinosaurs and a new chapter opened. But how exactly did those first recovering ecosystems function, and which creatures wrote the opening lines of that new age? Those first recovering ecosystems were fragile, improvised, and utterly transformed. The vibrant, late Cretaceous world we began with, filled with colossal herbivores and the biggest creatures to ever walk the Earth, had vanished in a geological instant. One moment, forests echoed with the calls of hadrosaurs and the footfalls of Tyrannosaurs. The next, a rock from space, reshaped the fate of life. We followed that rock as it tore through the atmosphere and struck at Chicxulub with the power of billions of nuclear bombs, releasing a fireball that vaporized land and ocean alike. We watched shockwaves race outward, mega tsunamis climb onto continents, and molten ejecta rain back down to ignite a global firestorm. When night finally fell, it was not a normal night. It was a shroud of dust, soot, and aerosols that blotted out the sun, plunging Earth into an impact winter. In that first night, temperatures crashed, photosynthesis stalled, and toxic rain washed over a silent, smoking planet. The age of non-avian dinosaurs was already over, even as their bodies still lay warm on the ground. Yet we also traced the survivors: small birds huddled in the dark, mammals sheltering in burrows, crocodiles waiting in murky water. From those scattered pockets of endurance, a new chapter of evolution began to write itself across an emptied world. This is more than an ancient disaster story. It is a mirror. The asteroid was a single catastrophic event, but its consequences unfolded over years and centuries as ecosystems collapsed and slowly rebuilt. Today, we are driving changes of comparable magnitude, not with one impact, but with billions of daily choices. Habitat loss fragments forests as thoroughly as any firestorm. Climate change alters temperature and rainfall on a scale that rivals past upheavals. Biodiversity decline is quietly assembling its own extinction pattern, species by species. Before humans, before cities, before history itself, the Earth belonged to giants. Not just big animals, but true titans that defined an entire era. Their disappearance set the stage for mammals, for birds, and eventually for us. Now, for the first time, a single species understands how fragile that stage really is. We know how impact winters work. We can read extinction in the rocks. We can see how resilience arises from diversity, from intact habitats, from stable climates. The dinosaurs could not choose their fate. We can. That is the difference that defines this moment in Earth's story. We are no longer just passengers on a restless planet. We are engineers of its future conditions. Will we be the asteroid of this age, or the guardians of its recovery? Join us as we keep exploring these turning points, as we step back hundreds of millions of years to understand the risks and possibilities of our own time. Support the science that uncovers these ancient nights, and the conservation that protects the living lineages they made possible. And when you look up at the night sky, remember, somewhere out there, a rock once fell, ended a world of scale we can barely imagine, and gave us the chance to decide what comes next.